Yes, thank you, Sanji, for this introduction. So I'm Anthony Larcher from Le Mans University, and I'm glad to be here to start this presentation from the multilingual speech-to-speech translation for under-resourced language team for this GSOL 2022. So this afternoon, we are going to talk about speech-to-speech translation, and especially focusing on under-resourced languages. So the task of speech-to-speech is quite easy to describe. You speak in one language, and then the system is supposed to try to translate your speech in another language while producing an acoustic signal. But what we were interested in this workshop is also to try to keep some paralinguistic information. For instance, that the system can produce voice with your identity or with your emotions while translating. And also one strong point was we wanted to enable this technology for under-resourced languages, or at least to work in this direction. The first thing that comes when you look at under speech-to-speech translation is that we lack of resources, and it's even true for well-resourced languages. So whatever language you work on, it's very difficult to find resources with aligned speech in source and target languages. And so that's one strong limitation of the technology at that time. One way to leverage this issue is actually to work with cross-modality. So if you can, instead of training just with speech data, if you can add some text data and then learn at least the translation, some information about the two languages using the text, then that means you can get more information, and that can benefit from your speech-to-speech application. Of course, the other direction you can take is also to leverage this information from different languages. So on this picture, you have two source languages that you want to translate to the same target language. You can also have the other way. That means one language that you want to translate in many languages. So by using many languages, your system might be able to learn something about the structure of language. So if you combine both, and that's what we try to do this summer, then you can leverage information for different languages, so cross-linguality, and also different modalities. You can use text and speech. But the thing is, if you want to use all this data, then how best can you mutualize really the knowledge you learn from any language or modality? So the assumption we've made, which is a strong one and that might not hold eventually, is that there exists a space that we call the common cross-modal and cross-lingual space, in which you can actually represent all languages in the same area. So for instance, you have one sentence in French, in Chinese, in German, and when you encode this information, your system will eventually end up with a representation that is language and modality agnostic. And then if you get this to work, then it might be easier to decode to another target language by using this shared information. And actually, the benefit of this approach will be that if you learn exactly this space, then after it might be easier to bring some under-resourced languages and just to make it fit in this common framework. So back 6 weeks ago, where did we start from? So about the context and the question. So what did we have at that time? Well, the first thing we didn't have actually is the data. So for instance, we choose to work with Tamashek language. Tamashek is a low resource language according to our standard. And it's a language from Africa that is spoken in different countries. So Alejandro will tell you more about this later. But just to give you an idea, we had a speech in Tamashek and translation in written French. No written Tamashek at that time for us, and no aligned speech data. Yeah. So the other point from the technical part, actually, we started from multilingual text modality. So we assumed that we had the LabC system, and this system is able to encode different languages in their written form into a space where they share the semantic information. So if I say, bonjour, je m'appelle Anthony, or hello, my name is Anthony, then the system will bring these two sentences in the same space at the same place. But the thing was now how to include the second modality, how to make speech fit in this space. So before the workshop, some of our participants, Antoine and Samir, developed this SAMU XLSR system, which actually relies on the LabC encoder. And what they did is that they tried to pull the XL-R system toward the sample representation that LabC is obtaining. And so they tried to keep this textual representation of semantic and to make the speech fit in this so that the encoder brings the information to the same place. So a little bit more in detail, but you'll learn more about this system during the presentation. What they did is that on the lower part of this picture, you can see the LabC architecture. This one was frozen and just used to guide actually the XLSR part, which is the upper one. And what they did is they used the XL-R system. They add an attention pooling, then a projection, and hyperbolic tangent activation. And the point was to be able to project one sentence of speech at the same place as the same sentence in text. So it has been trained with 51 languages at that time using Common Voice, and the alignment was only semantic. And so this is the same ID, just with a graph. And at that time, so 6 weeks ago, when the story started, we didn't have any decoder for this. So we were just able to project speech and text at the same place in the space. And this has been validated by experiments on information retrieval. And just a reminder is that the alignment in this space was done using only semantic information. So that means at the sentence level. So what we have been doing and what we are going to present today with all the team is first some analysis of this space. So we've been analyzing how the SAMU XLSR work for to model the semantic information. Then we focused on the family of languages, assuming that some languages are closer than others. And so how does this representation space behave for different families? And also, what kind of acoustic information does this encoder keeps actually in the representation to understand what we have in this common space? Another part of the team has been focusing on extending actually this existing work in order to disentangle the modalities from the common space, so to produce a decoder to generate speech and text. And also to build a common space by assuming different loss actually. So aligning the sequences of embedding instead of working at the sentence level in order to try to keep richer information. Another part of the team has been working on pre-training language models for low resource machine and speech translation, focusing on the text modality, but applying it also to speech to text. And eventually, we had people working on SAMU XLSR to add the multimodal speech-text capabilities for translation. The last point actually is about evaluation, because when you come to speech-to-speech translation, usually people use the text modality to evaluate it. And when you lack resources, actually, you don't have resources to evaluate either. So if you don't have text, you cannot evaluate with text. And so part of our team has been working on developing metrics to evaluate the speech-to-speech translation without relying on the text capacity. So now I will let the microphone to Valentin, who will talk to you about the semantic extraction.
Thank you, Anthony. So now I'm going to talk to you about how does the SAMU XLSR speech embeddings perform on cross-lingual semantic extraction. So in the context of the analysis of the common space, some new questions were raised. And so one of them was whether the SAMU XLSR embeddings contains enough information in order to do cross semantic extraction, semantic information extraction. One other question was whether the SAMU XLSR embeddings were truly cross-modal compared to LabC, but also cross-lingual between the different languages. And so in order to do that, we use the two different datasets to do a spoken language understanding benchmark task, the media and the Port Media datasets. The media is a French dataset and Port Media Italian datasets that are human-machine dialogues in the context of hotel reservation. And those datasets are annotated with concepts and semantic information that we call concepts. One thing that we can note is that the media and Port Media dataset are quite small, even more for Port Media, which is even four times smaller than media. And when we look at the semantic annotation, we have three kind of annotation. So we have the word support, which is the transcription of what has been said. And then around that, we have the concepts that tells what those word supports are about. And then the value, which is normalization of those words. So, for example, in I would like to book a double room in Paris from the 8th until the 16th of August. I would like to book will be a task that the user wants the system to perform. And we could normalize would like to book to reservation so that the system can know what to do. For the metrics on those datasets, what's generally used is the word error rate for the transcription part. And for the semantic part, it's the concept error rate, which is the word error rate, but applied to only the sequence of concepts. And then I'll give the mic to Gaël.
Hello everyone, my name is Gaëlle Laperrière. I'm first year PhD in Avignon University in France, and I will take the lead from now. So the question was, how does SAMU-XLSR speech embeddings perform on cross-lingual semantics extraction? And we also want to compare the efficiency of the original XLS-R compared to the SAMU-XLSR and see if the fine-tune done on SAMU-XLSR, thanks to LabC, improve the capacity of the speech encoder to better extract semantic information, even for a cross-lingual task. To do so, we use this architecture. It takes wave signal as input and generates a sequence of characters. And we use frozen and fine-tuned speech encoder, which was XLS-R or SAMU-XLSR. We did an analysis of the layer-wise frame-level embeddings. That means that we analyzed the embeddings generated by each of the 24 layers of the XLS-R and SAMU-XLSR. We also wanted to see the language portability of both encoders. So we did some zero shot, which means that we trained on French and only tested on Italian, which is lower resource. And also some low resource training, thanks to media or media then Port Media training. So here are the first results. You can see a chart of word error rate evolution. So we wanted to get down because it's an error rate, considering the layers of the embeddings that have been extracted from the speech encoders, both fine-tuned or frozen. The first point is that SAMU-XLSR outperforms XLS-R for the media transcription because, as you have seen before, we also have the transcription of the data, so we can see that here. And the second point is that a best word error rate is achieved by higher layers for SAMU-XLSR than it is for XLS-R. Here you can see another chart, so it's the same but with concept error rate, so we are only looking at the order and the presence of the concepts. First, we can see that XLS-R lost almost 7 points between its best layer and the last one, but SAMU-XLSR only lost 1 point when frozen. So this means that the SAMU-XLSR is tuned to keep semantic information until the end, but XLS-R initially is only tuned to minimize the contrastive loss. So it does not keep the semantic information until its top layers. So yeah, we can say that SAMU-XLS are capturing and encode the semantics better for our text, even if when fine-tuning those, we can see that the semantic information is kept. So here some results about zero shots for language portability. We did this experiment to see the efficiency of language portability of SAMU-XLSR after seeing only French data during the training. So when testing on Italian, SAMU-XLSR is designed, we can see that SAMU-XLSR is designed to extract semantics better than XLS-R, but it is not designed to produce language-dependent embeddings for speech transcription, especially when seeing another language. So on the top right corner, you have an example of what we were expecting to have and what the model generated. So we wanted to have the concept answer and the sentence "si grazie," but we only had the right concept, which was great, with some French Italian words saying "oui merci." So maybe we can later on see what that means and maybe doing some translation. And another point is that fine-tuning the SAMU-XLSR on French degrades the Italian embeddings quality. We can talk about multilinguality loss because SAMU tries to adapt to French and lose memory on previous learned Italian or other languages. Some results about language portability for low resource. So we wanted to see if language portability was great when training on low resource languages and see if the French dataset can help the Italian SLU task because we trained on media and then we trained also on port media for the same architectures, for the same model. So first time use outperform XLS-R semantic extraction and speech transcription, which is what we expected. Fine-tuning XLS-R on Italian degrades the performances on Italian, which can be because of the type of data, because it's phone calls and XLS-R was initially pre-trained on Common Voice. So it's also not the same domain. And we are minimizing the concept error rate and not some ASR task. Also, fine-tuning XLS-R on both French and Italian enhances the performances on Italian by far. And last but not least, fine-tuning SAMU-XLSR on French prevents good Italian word generation, like you saw before, but enhances the semantic extraction, and that's what we wanted. Thank you.
And we wanted to compare all those the SAMU-XLSR embeddings compared to the LAPC text embeddings. And the way we did that was to use the sentence embeddings of SAMU-XLSR and combine that with the sentence embeddings of LAPC. So we trained a model either on SAMU-XLSR frozen sentence embeddings or LAPC sentence frozen also sentence embeddings. And we train our model to detect a bag of concepts. So before our models were supposed to predict a sequence of concepts. Now we are switching from that representation to just multi-hot representation, listing all the concepts that are currently in the given segment. And we are showing the results with the micro F1 score. And we also are comparing those results with the results Gal showed you earlier. The only thing we did in order to compare that was we converted the output from the previous model to a bag of concept outputs. And so one thing that we can note is that when we train on speech embeddings, so SAMU-XLSR, and in French with French data, we can get some really good results with the LAPC text embeddings. So that means that the SAMU-XLSR embeddings, the sentence one, are really close to LAPC embeddings. Then when we test it, we can see that the LAPC embeddings are able to perform better than the SAMUX-LSR embeddings when we just train on SAMUX-LSR, test on SAMUX-LSR, or train on LabC and test on LabC. And also, we are also able to get some really good results on the SAMU XLSR embeddings for the Italian. So we never trained on Italian, and we are able to get some good results. And actually, those results are better than the one given with the previous model that works on the frame level embeddings. So that means that sentence level embeddings are better able to grab the semantic content, cross-lingual representations. And so to conclude, we trained some spoken language understanding benchmark model on both frame level, sentence level embeddings, but also on cross-modal and cross-lingual inputs. We can see that the SAMUX-LSR is able to get semantic information up to its last layer. Also, SAMUX-LSR embeddings outperform the XLSR embeddings when compared to the semantic extraction and speech transcription tasks. When switching from higher to lower resource with pre-training, we cannot get some good results with on the transcription, but we are still managing to get better results on the semantic extraction task. And for when we train on the sentence level embeddings, we are able to get better results than the frame level embeddings for the cross-lingual tasks. So now I leave the mic to Tomatibo.
So hi everyone, I'm Tomatibo, a PhD student at Le Mans University. I'm gonna talk to you about the analysis and the work we did on SAMUX-LSR applied on different language families. So first, what are we talking about? Here we are presenting works on translation models. So most those translation cross-lingual models are trained on multiple languages, a lot of them actually. So one of the first things we did when we arrived was to look at which languages were actually used in their pre-training, if there were intersection between those sets, and what were the characteristics of those languages, the amount of data available by language. So here you have an example, a dendrogram of the different family that the different languages that were used for training SAMUX-LSR, and they are classified using families and subfamilies according to the ethnologue classification. And you can see that already one thing that's striking us is the huge majority of languages are from the classical Indo-European family. You have English, for example, that's our main point with here for SAMUX-LSR, 70,000 hours of speech, compared to, for example, the Berber subfamily. That's the one containing Tamashek that we are especially interested in. That only contains 500 hours, so that's a bit unbalanced. Of course, during the training, the system were used sampler that balance the data, but it doesn't change the fact that you have the system can see a much more variety of languages of data from different languages. So one of the first things we did was also to look at the different amount of data used by LabC and XLSR, XLS-R. So here you have a plot that represents the amount of sentences used for training on LabC and the amount of hours of training for XLSR for different languages, and the color are related to the families, except for the blue ones. Those were the ones that were alone in the family. So you can already see you have clusters of higher and lower resource languages that are not necessarily classified by family. If you look at it in a family way, you can see that you have huge differences between them. So that was one of the main motivation to look at family-specific models. So one first thing we did is to look at how the model behaved for different families, for different languages, by comparing its embedding. So basically, SAMUX-LSR is a fine-tuned, improved version of XLSR. So we wanted to compare the embeddings before and after the fine-tuning. and it's made to get closer embeddings to LAPC. So we also wanted to compare embedding to LAPC. So SAMU XLSR is a version of the XLSR model, where the framework embedding were pooled using some attentive pooling to get sentence embedding that can be then comparable to LAPC embeddings, because LAPC is a sentence embedding model. So here we compared two metrics. That's a bit basic, but that had allowed us to perform some analysis without depending on a downstream task, but directly on the embedding produced. So the cosine similarity between the sentence embeddings, so it's a similarity, the higher, the closer. And so that's SAMU XLSR. And the mean cosine similarity for the framework embedding frame by frame. And here I must just warn you about this. This part we measure because XLSR and its fine-tuned version for SAMU have the same architecture. We have the same length for the sequence, so we can do embedding to embedding comparison. But this does not ensure us that the embeddings are in the same order before and after fine-tuning. So we might have a different order in the embeddings in the sequence, and that might get us some much lower cosine similarity. That's what we're going to see in the graph just after. So talking about the graphs. So here we have some interesting observation that may seem obvious at first, but on the left, you have the graph that's comparing the number of hours of training for each language for SAMU XLSR compared to the cosine similarity between the embeddings of LAPC and the embeddings of SAMU. So we wanted to see SAMU is trained to get closer to get embeddings that are closer to LAPC embeddings. And those embeddings, if the training is going well, they are supposed to get closer and closer. So to have the cosine similarity that's getting higher and higher. And that's what we can see in the graph with the purple arrow. The more you train the language, the more closer embedding gets. And it's the opposite way for XLSR. You get some embeddings that are less and less similar to XLSR embeddings as much as you train the language. So it's it's kind of confused here because you have a lot of languages, but you can still see the tendency, but still no family-specific clustering that can emerge from those graphs. So we took the decision to make ourselves some specific version of SAMU XLSR by family. So we train those different versions on subset of languages by hoping that this would improve the performances for the language on which they were trained. So what are those languages? We selected some subfamilies. So we have 4 Indo-European families: Italic, Germanic, Balto-Slavic, Indo-Iranian. And we also took some subfamilies from different language families to see if we could get better performances. You can see that at the end you have especially the Afro-Asiatic one. That contains only one language because that was the only Berber language we had, and Tamashek is also Berber, and we want at the end to be able to perform some tasks on Tamashek, so we trained one model especially on KB. So what did we do exactly? So XLSR basically is a wave-to-wake architecture that has been trained on a lot of languages that give us an XLSR-based model. That model has been trained on a much lower, much restricted set of languages. That's the one that were common between Common Voice 8 and the LAPC training set. The language is common, not the data. LAPC is text. And so that gives us SAMU XLSR. That's a version that is closer to LAPC. And by continuing this training with another training set that's getting smaller and smaller here, just the few languages from one family, we get a family flavored version of SAMU XLSR. And we did that for the seven different family I showed you just a slide before. So then once trained those models, we fine-tune them on 2 downstream set tasks. One about the Tamashek to French translation using the IWSLT 2022 dataset, the 17 hours of Tamashek we talked about earlier, and one on a SLU task, so concept extraction on the French dataset media. That is exactly the same task Valentin Gael just talked to you about a few slides before. So we try to fine-tune those models on those tasks to see, for example, if the Berber or the Italic model will provide better result for Tamashek to French, and if, for example, the Italic model will perform better result on French. because French is part of the Italic family. So let's get the first results. So at first we just compare the base version with the Berber version for translation. So here we are measuring a blue score. So the higher the better. And we can see that even if at the start of the training you have really close performances on the validation, you can still see that the Berber version is getting outperformed by the base model. So no improvement here. Out of curiosity, we tried with all our flavored model because it was trained. Why not try it? And it's a bit confusing here. So we actually have a lot of models that have similar results. The base model is still the best one. We were expecting the Berber one to be the best out of the different flavored model, and here it's the Indo-Iranian that get first. So surprising, but we're gonna get back to that Indo-Iranian model later. So keep that in mind, and yeah, still no improvement for language-specific models. So the base model trained on more languages is still the best. Then the SLU task. So the SLU task here, we are evaluating this on concept error rate. So here, the lower the better. And we got here the best model that was not the base one. It's the Indo-Iranian one. Even if we were expecting some interesting results from Italy, we still got Indo-Iranian that's also the best, even if it's trained only on 2 languages that are not at all from the same family. Still, I must warn you about those results. I mean, even if this one seems to be the best, we have a confidence interval that's large enough to consider those results as not significant. So we cannot really say we have an improvement here on the baseline. So now we wanted to push a little further on the analysis to understand why do we have so poor results, why do the Indo-Iranian model perform so well. So we came back to our cosine similarity metrics to measure the distance between the fine-tuned model and its original model for the language that were used for pre-training and the language that were not used. So data set a bit larger. And here I'm gonna present this. So those are the 2 graphs that are interesting here. The left one is the sentence embeddings from SAMU-XLSR that were compared to the sentence embedding from LabC. And for the 2 axes, the x-axis is for the in-family languages. Are they similar to the language to which it was trained? And it's expected because you are training them to be closer to get closer to LabC. And the y-axis is for the out-family languages. So is that do we have a generalization here? And for the right graph, we have the exact same thing, but with XLSR, and we're expecting to get further and further away from XLSR because we're training from XLSR to get something new. So we're expecting the embedding to shift from XLSR, so to get a lower cosine similarity. So that's the point for the SAMU-based model. And now we're gonna see the same thing, but with all the different flavors. So for each flavor, you have the in-family set is the family that was used to train the model, and the out of the main family is just all the other languages. So we computed again those cosine similarity for all of those models. And sorry, okay. And then we could observe a few interesting things. So let's first focus on the LabC graph. So what can we see? The first thing is that all the points you see are under the x equal to y line I plotted here. So obviously you have a better similarity for in-family than for out-family. Makes sense because you are trained on the in-family, so you are supposed to get a better similarity. Then second, you can see a shift toward a better in-family similarity. So by training it a bit more on less languages, you get better similarity for your family. And then for generalization, here you can see that depending on the family, you get better or worse out of family performances. And the 2 points that are interesting here is the lower one, it's the Berber one that got the worst results. Might explain why we didn't get anything useful from it earlier. And the best one, the one that got maybe the best generalization because it got closer to out family languages, is the Indo-Iranian one. That might be a first element of explanation. And then we did so again to the same thing with the XLSR graph. So here we compare to XLSR. So the more it's trained, the further it's supposed to get away from XLSR. So here, almost all the points are over the line, so it's getting further from in-family language than from out-family. Again, it makes sense, but except for the Berber one, that's an outlier here. That's also maybe an explanation of the performance of the model. And we get from SAMU a global tendency for all the model to get a lower cosine similarity. That means that by training them more on more specific language, they got further from XLSR. Except for, and that's interesting here, there is one family of language, the Indo-Iranian one, that managed to get closer to XLSR. The cosine similarity was higher than for SAMU from the base flavored model. So we have the Indo-Iranian is actually the only one that got in the same time closer to LabC and closer to XLSR embeddings. So, and that's also the one that got the best results for the previous task. So maybe we should do something with that and use the loss to keep some information about the basic XLSR model. Again, that's a quick analysis on what happened for the different models, but that's a visualization. So quickly, what to take away about those different families. So the first thing, kind of obvious, but we have huge disparities in use between the languages. So the number of hours available is going to impact the cosine similarity of the embeddings. So obviously it's going to impact the behavior of the model. So to get a bit better result about this, we trained some specialized family-wise models and fine-tune them on 2 tasks. Sadly, we do not have breaking, state-of-the-art results, but we still got some interesting results for the Indo-Iranian family. So we're going to try it on a translation test, for example, for Indo-Iranian, and that's going to be the future works to try it further on the language on which is supposed to be the best. And for the int and out domain analysis of embeddings, we get some interesting results still with the Indo-Iranian and expected one for the shift of embeddings, getting closer or further away from the model we were supposed to train. So kind of still makes sense. So now, Natasha, I'm letting you.
Hi everyone, I'm Natalia Timoshenko from Avignon University, and I will present just a few slides to conclude this comparative analysis of the encoders. And in this part of the presentation, we will quickly demonstrate a few additional experiments that help us to understand better what happens with the model when we try to fine-tune XLSR model with a semantic constraint. We would like to verify if it is in line with our intuitive understanding and expected theoretical assumptions that during the training, the information that does not help the losses is removed from the model. In other words, if the model is trained to extract semantic information, then irrelevant for this task acoustic information will be removed. To do this, we train several tasks such as speech recognition, speech emotion recognition, speaker identification and verification, and also automatic speech recognition, and some others. And on the speech representation from different levels of XLSR and some XLSR models. So we'll demonstrate a few selected examples from the experiments we did. And the speaker identification task was performed in the super benchmark style. So we use a simple classifier on the top of XLSR and some XLSR representations taken from different hidden layers of these models. This illustrates the reducing ability of some XLSR model to discriminate speaker information, especially when we go to the upper layers. And we observe similar results when we train automatic speaker verification systems with state-of-the-art architecture. For the next slide, we can see the results of speech emotion recognition experiments on the multimodal emotion lines dataset. The task is to classify emotions into 7 classes, and the black line shows the differences between XLSR and some XLSR performance in F1 score. So even if the results are quite noisy, we can see that there is some trend in suppressing of the emotion information in the some XLSR model. And finally, in this experiment, we use a hybrid TDNF acoustic model for the speech recognition task. This model has a relatively short context and does not rely on semantic information, for which its decoding time as an external language model is used. And that's why we use this model to demonstrate that the amount of acoustic information is reducing when the models are fine-tuned with a semantic-oriented objective. And it is decreased when we go to the upper layers. Some XLSR model is not good for such ISR systems that don't capture semantic information, in particular for hybrid acoustic models. However, for end-to-end acoustic models, it can be useful if you don't rely on the external language model, and especially for the low resource languages, as was shown in the previous presentation by Gael. And so, as expected, the SAM XLSR model that was trained to extract cross-lingual semantic information suppressed most of the acoustic information in speech representations. And this requires to integrate additional mechanism into our end-to-end speech-to-speech translation model, and that help us to pass speaker and other relevant information into decoder and into vocoder. And we would discuss it more into the following sections. And my talk will continue, Henry. Thank you.
Hi, everyone. My name is Henry Lee. I am a PhD student here at Johns Hopkins University. And for the next 10 minutes, I'll be giving a brief overview of the language and modality disentangling decoder that we worked on during this workshop. So in our proposed encoder-decoder architecture for speech translation, the encoder maps multilingual and multimodal input speech and text onto a common representation space that is supposed to be language and modality agnostic. Subsequently, the decoder would have to map from this common representation space onto a specific text or speech in the correct language and modality. There are a number of ways that this can be achieved. One of the more common way is to have one single decoder for each language and modality pair. So as is shown on the left, that's what most previous work have focused on doing. Whereas our approach is slightly different because in many low resource scenarios, we would like the low resource languages and modalities to be able to leverage as much knowledge and as much information from the higher resource language and modality pairs. So we would like the system to be able to share as many parameters as possible for as long as possible until it finally branches out into the what we want. So as such, we introduced the pipeline for our decoder, as shown here. From the common representation space, the embedding first passes through a modality and language disentangling decoder that is shared across languages and modalities. The target of this decoder is any of, the target of this decoder is a space that previous studies have shown is easy to generate text or speech from. So, for example, in the far left, the space that we generate English text from. In our case, we chose XLM Roberta because we know that there are previous studies where generating text from there would be possible and in some ways easy. And the one that we chose for generating speech was XLSR for the same reason. Next, we will discuss the architecture of our decoder. It is simple enough, I guess. It consists of two parts, a transformer decoder and an optional vector quantizer. The transformer decoder takes the output of our encoder as memory. The target embeddings, so for example, XLMR or XLSR in some of our experiments, just to give an example, are the targets. Prompts are appended to the target, which are essential for letting our decoder know where to map our input into. The prompts include the target and target language and modality for obvious reasons. The source language and source modalities, that is to account for the potential imperfections in our encoder space, because the assumption is that the encoder output should be language and modality agnostic, but that may or may not be 100% the case on all occasions. And finally, a predicted target sequence length, something that I will go into slightly more detail in the next slide. The quantization layer is, well, as I said, optional, and it is used because our vocoder takes a finite discrete set of tokens as input. While we could discretize our output after the fact with methods such as k-means clustering, we find that having the decoder learn it would give us performance benefits. Next, I will give a brief introduction on the length prediction or length estimation. Our decoder needs to know, well, any decoder would need to know when to end sequence generation. The common way to do it in NLP is to have a special end of sequence token, and for the model to stop generating when the end of sequence token is reached. Well, the same approach could be used for generating speech or generating embeddings. It is a little bit tricky to find an appropriate end of sequence representation in a continuous space, or at least that's what we found during this workshop. So we introduced two methods for helping our models generate sequences with appropriate lengths. We base our first approach, the one on the left, on a system that was proposed first in the Tacotron 2 paper. We add a sequence termination gate to our model consisting of one linear layer and one sigmoid function. It is the square that is on the bottom left of the colorful embeddings. On each step, the vector that is generated from our decoder gets passed into the termination gate, and it outputs a logit that represents the probability or likelihood of the sequence generation terminating on that step. The training target for the output of the termination gate would therefore be zeros up to the point where the sequence ends, and then 1 onwards. We find that this module, while not exactly perfect, does help our model generate sequences with reasonable lengths that correlate more or less with the target lengths of our sequences. One weakness with this approach is that the decision to terminate generation is local. As such, we propose our second approach, a transformer encoder based duration estimation module that takes into account the global information from the entire sequence. It takes the encoder output as input. After the input passes through the transformer encoder, it goes through a number of pooling layers, which eventually gives one number, that is the predicted sequence length. And that number is trained against the actual sequence length. We find that this system was able to produce very accurate estimations of sequence lengths, and the output is therefore the output can then be used as one of the prompts to our decoder, which helps our prompt get a global idea of, or like get some idea of how long the target sequence is supposed to be. So my colleagues will now introduce the subsequent parts of the decoder, namely the text coder and vocoder, which will actually generate interesting things like text and speech.
Hi, my name is Marek Sarvaš, and I'm master student in Brno University of Technology, and I will briefly talk about what text can we generate from our decoder embeddings. So as Henry showed, this is the whole decoder pipeline, and I will briefly talk about the text generation part. So the main goal is to produce text from the modality disentangled embeddings from our decoder in target language. And as the main part of the decoder were built, our initial experiments were done on the embeddings from XLMR encoder, as these embeddings were the target during the decoder training. We used different datasets as LG speech and common voice. LG speech was used also for training the decoder, and common voice to try multilingual settings. And we also tried some architectures, such as only transformer with only decoder layers, BILSTM model with only CTC loss as an objective, and transformer encoder decoder. The transformer encoder decoder architecture had best results. We used linear projection layer at the beginning to reduce the size of the embeddings and edit language ID so we can generate target language. This was trained firstly separately on the common voice dataset for these 4 languages, English, French, Spanish, and Portuguese, and we got pretty good results on there. So after verifying that we can generate good text from this, we moved to the embeddings from our decoder. As our preliminary results shows, we can also generate decent quality text from the disentangled modality embeddings from previously trained decoder. And those are only the first experiments, so on smaller data samples. And for our future goals, first thing is to fine-tune together the decoder and text coder and on more data, and also introduce more languages to train the whole pipeline in multilingual settings.
So, hi everyone, I'm Thibaut Gaudier, PhD student in Le Mans University, and today I'll talk about the speech generation from different representations, since that's the topic we worked on with Jared. So, first of all, for the big picture, we're working on the speech decoder. So the point is to generate speech from the modality disentangling decoder output, which takes itself its input from the common multilingual and multi-modal representation. So the point is, in the end, to produce speech, but we do not have text to perform like classic text-to-speech synthesis. So we had to do a few experiments to see how it works. So first of all, the point was to generate text from the different. So what we tried was generating text from different embedding spaces. Some of them are extracted from speech, and some other from text. This leads to different issues since embeddings from text are closer to text, for example, in their duration, while embeddings from speech might already have the good length, so we do not need a length predicting module. And about the models we use, so we tried to use different systems. Mostly in 2 categories. The first one is a TTS model, which is usually used to generate the speech from text, and a vocoder, which usually takes its input from some speech-related features, such as a mail spectrogram. And what the answer we wanted to answer was how can we generate speech, and how can we help the speech generation, for example, by using different kind of embeddings. For example, one embedding for coming from speech and one other coming from text to help the generation of speech in the end. And another issue we might want to solve at some point is the control of the speaker in the identity in the generated speech. So that's one other thing we tried. For the features, so we used different features. So some of them are extracted from speech, some of them from text. Each of these features have some benefits and some drawbacks. For example, WaveLM, it's basically our starting point. We started with that. But it has major drawbacks for our experiment, since it's neither multimodal or multilingual. It's only trained on English speech. SAMU-XLSR were the embeddings that were presented a bit earlier, which are extracted from speech. XLSR are multimodal, multilingual, sorry. mHubert is the multilingual version of Hubert, and Speech T5 is a multimodal decoder only in English, but which can produce embeddings from speech or text. And for the text-related embedding, so we tried TTS for TTS, so taking raw text as an input, but also some other embeddings such as LabC, which have been used to train SAMU-XLSR embeddings, XLMR embeddings for cross-lingual text, and Speech T5 text embeddings. So for our model, the context was to produce speech from modality-specific embeddings. So we have, from the modalities entangling decoder, some embeddings which are well suited for speech and some other well suited for text. So what we wanted was to adapt some TTS model and some vocoders to generate speech from these embeddings. The models we used for the text-to-speech models we did adapt, we used Tacotron2, which is a pretty classic now TTS model, and also Transformer TTS, which is pretty close to Tacotron2, but which uses transformer, encoder, and decoder layers. For the vocoder, we used the Hi-Fi GAN, which is a widely used vocoder, which uses generative adversarial networks for generating raw audio from spectrogram. And so we did some adaptation that I will present later. We also wanted to extend some of the models to fit in our pipeline. For example, we tried, and we are still working on the transformer TTS, which would take 2 inputs and using cross attention to take as many information as we can from both modalities. So first of all, for Tacotron2, the main modifications we did was basically to change the input. The input in a regular Tacotron2 is text and some character embedding of text, and we changed it with the input, which could be text or speech, and a frozen feature extractor such as WaveLM or XLSR or any other, and just then train this system on to generate mail spectrogram from these embeddings. So depending on the embeddings, we got pretty different results. For example, for taking WaveLM features as an input worked very well. That was the first thing we tried, and yeah, it worked very well. But the others, since they add some more features such as cross-modality or cross-linguality, it does not work as well or as easily as WaveLM features. In the end, we also changed the vocoder. We used the WaveGlow vocoder, which we trained earlier, which performs very well and does not produce some bad speech. It's a really good speech in the end. So that's the modification we did for Tacotron2. Then for Transformer TTS, so that's as I explained earlier, it's a transformer-based TTS system, which we adapted similarly to Tacotron2 to feed it with some inputs coming from pre-trained models to generate mail spectrum also. So we also use WaveGlow vocoder for speech synthesis in the end. And the adaptation we are working on, so it's not yet ready, but we're still working on it, is the inputs coming from different embeddings and different modalities to help the speech generation, because for now it's a bit complicated to get some clean speech from this system. Then, so iFagan, it's a vocoder. So the point of it was to generate the embeddings directly. To generate the speech directly from the embeddings. So we wanted to, we used a few kind of embeddings, as you can see. But in the middle, we had to put some quantization layer. We used the K-means, we trained the K-means quantization from different embeddings to then train the iFagan vocoder on these embeddings. So now I'll let you listen to some samples. So this is a reference speech.
He graduated from Maryland University.
And then for different embeddings, so each one of these samples are coming from a different iFagan vocoder, which has been trained on the K-means extracted from each features.
He graduated from Maryland University. He graduated from Maryland University. He graduated from Maryland University. He graduated from Maryland University.
So as you can see, the result is very good. We can hear there are some differences, which even if the input signal is the same, the embedding spaces and K-means quantization are producing some variability, which makes the input a bit different in the end. But all of them are pretty clean speech, and so it's pretty good. It's very good good synthesis. Then what we wanted was to adapt this system for multi-speaker. So the point was to generate the samples. The generated samples would take the linguistic information from the input speech coming from speech C5 and the K-means quantization, but the speaker information would not come from the training of the vocoder, but from next vector or any speaker information representation coming from outside. So, for example, coming from another speech signal or anything. Then we wanted also to have it work with speaker embeddings coming from different languages, because the point would be to be able to train the vocoder with some embeddings in the target language and not on embeddings from the source language, speaker embeddings, because it would be harder to get some parallel data sets which would be well fitted for training that kind of systems. So that's the reason we wanted to be able to feed some speaker embeddings coming from another language. But as you will see, it's not working that well. So the source sample is
family members later on emigrated to the United States.
And then the speaker identity is supposed to come from this sample.
Plus tard, les membres de la famille émigrent aux États-Unis.
So this is a French sample, and the result is not terrible.
Family members later on emigrated to the United States.
So as you can see, we don't get the speaker identity yet. So it's still work in progress, and it's still something we're gonna work on the upcoming weeks to be able to generate speech from speaker embeddings coming from another language. So to conclude, the TTS systems, some systems which have been designed for doing text-to-speech are able to be modified to take some embeddings from some pre-trained models and still generate a very good quality speech. We tried some experiments with sentence-level embedding. So, for example, for LabC or Samuel XLSR, you just put one sentence and get one single embedding for the whole sentence. It does not work at all for speech synthesis. We need more information than that for the speech generation. We were able to generate speech from raw audio using a quantization layer, either coming from monolingual or multilingual embeddings, since we tried, for example, with Samuel XLSR or XLSR, and it worked well also. And there's not really information about the speaker in the quantized features. The quantized features only contains the linguistic the linguistic information and not the speaker information, and that's a good thing for multi-speaker speech synthesis, since it will be easier to generate speech for a single speaker. And so for the upcoming work, we would like to adapt the TTS system and vocoder system. So vocoder works well for now, but also for coming from different languages, to add some speaker embeddings in all the systems to be able to control the speaker information in the synthetic speech. We would also like to try to have a single model which would be able to generate speech in multiple languages, for example, by using prompting or language ID as an input. That's something we have to try at some point, but we did not really start about that for now. So there's a part about generation from speech and text embeddings. We think it could help the speech generation, and we'll have to see when the systems are ready. Also about the IFAGAN part, we wanted to compare for now we're using a discrete unit, so one hot embedding, but we might want to use some soft units by giving instead of one single value, giving a probability distribution among all the units. So that's one thing we will try to get some more control on the synthetic speech. And in the end, for transferring voice from input to output, we might have some work still for the multilingual setup to avoid using some parallel data, which is synthetic in some cases, such as CVSS corpus, where the different voices, so some voices are synthetic, so it's more complicated for speaker identification and speaker embeddings. Thank you. So yeah, some conclusion about the three last presentations from Harry, Marek, and myself. So we have the encoder part, which is on the bottom of the slide, the common multilingual and multimodal representation. So then these features are coming into a modality disentangling decoder, which will produce some embeddings which are specific to a language and specific to a modality. And using these modalities, we can use some systems such as a text decoder to generate text, or a vocoder or speech synthesis system to generate speech from these disentangled embeddings. Thank you very much. So now it's time for a cookie break, I think, and any question about all the presentation you've had at the beginning, if you want.
Yes.
Yeah, it's disentangled modality work. I wonder how you define the disentangled. That the disentangled modality. Because mostly we talk about disentangled. It's orthogonal. You want to separate the signal. I'm not sure the detail.
Okay, so the disentangling can be confusing here. So actually, there's no. The decoder is just trying to produce one modality, something that is closer to one modality or another one. But actually, there's no mechanism within the decoder that really disentangling the information in the sense of VQ, VAE will do it. It's not relying on this kind of thing. It's just based on the prompt that we introduce in the system. Yeah.
More like conditional.
Yes. Yeah. Definitely. Yeah.
You should repeat the question.
Sorry, excuse me. Yeah.
Okay. Kevin has a question.
Yes.
Hi. Hi, can you hear me?
Yes.
Okay. So I have a question about the SAMU embeddings and how it's trained for the family-specific training. So my understanding is you have the LabC embeddings that are already fixed, right? But then you're taking smaller subsets of speech and their associated transcripts when you do the family specific training.
Yes.
Okay, so I guess the question is, does it make any sense to focus on the lab C part 2 when you're doing family specific training? Because this is, you're doing a translation task as well, right? So you're kind of reducing the speech data, but you're not touching the translation part.
Yeah. Yeah. So yeah, actually, we didn't want to. We wanted to just look at the behavior of the embeddings totally independently on the task, and even if we do not use translation data and only speech with its translation, we still have variation in the position of the embeddings, but in the way they are similar to LabSys one. Because here is basically just forcing an alignment with LabSys embedding totally independently on the translation. So we were not expecting to get eventually. I mean, yeah, that was we did not expect specifically improvement or not for translation. We just wanted to know what impact it could have to have a language specific fine tuning.
I see. Okay.
Yeah.
But,
yeah, sorry. And if I can add something, you will see in the second part that actually for the decoding part, so as soon as you want to generate text or speech, you will improve a lot the performance if you really train the encoder decoder part as a whole. So that's something also we didn't do at first for the evaluation of the language families, because this work has been done on the initial encoder without having the whole pipeline plugged together. So definitely there's something to dig in the future.
I see. Thank you.
Yes, Shinji?
Yes, I have a question about the language family analysis. I actually enjoyed it. And but if we consider the spoken language similarity, we have various other kind of metrics, right? Geographical one, genetic one, or even some people using language vectors to consider similarity. So I just want to have a comment about whether you guys are plan to apply it or already have that, or yeah, I'm just curious about that. Yeah.
I think, here our definition of the classification of language, we were really focusing on the way ethnologues classify the languages. So I think it's an historical classification. So I don't think at all it has any impact on, for example, the phonetic aspects of the languages, because you can take two languages from limitrof countries that have totally different historics, but are still quite close in the way people pronounce them. Still, maybe there is obviously a link between geographical and historical classifications, because people are moving across the age. So yeah, I think it's not a perfect separation or classification of the languages, but that's one we wanted to explore, and that's certainly one of the questions we wondered at first when we had to find a classification. Could we find some different metrics, some different way to define languages, as you have accent, as you have more interesting features? So that would be one of the remaining works question.
Okay, thank you so much.
Thank you.
Yes, please.
Yes, I have a question on the multi-modal decoder. Very interesting. So let's say, for instance, like getting the same audio, but I decode it once with the text box, and then decode it the second time with the speech model, provide the two automatic where they can be.
So if I understand well, your question is if you provide different modalities for at the input, will you get the same output from the decoder, right? Is that your question? And so. So we don't have the results on this yet. Actually, that's something we need to keep working on. Yeah, but that's a very good question. Yes, there was another question.
Evelyn has one.
Yes, please.
Evelyn?
Yeah, Evelyn.
Oui.
Yes.
Can you hear me?
Yes.
Okay, so thank you for all those presentations. Extremely interesting, and I am very sensitive to the complexity of the multiple tasks. I work in a world that people ask for data and tools that are ready to work. And I understand that all that you presented is the state of the art in research. But if I were giving you a set of sentences in Tamashek, how close would you be able to provide me with the English translation, either audio English or written English? I know it's a very hard question to understand because it's how far is it from the training and so on and so forth, but yeah. Have you done any hands-on experiment of that nature?
Yeah, so actually you will have some numbers in the second part of the presentation. This will give you an idea of the quality of translation. After, it will be the question of the quality of the metrics. Bleu for translation, that's something else, but definitely you will get some number and you'll see that we have a great improvement with the data we have in Tamashek, for instance. So it's improving. I will not spoil now, but you will see that it's getting better for Tamashek, and we can expect this to be reproducible for other languages, I think.
And when is that presentation going to be? Right after the break or when?
So it's the last part of the presentation, so it will be 1 hour after the break. I think that you will see the results.
So at what time is it starting? I'm just asking because it was not.
It starts, so the second part starts in 10 minutes.
Oh, 10 minutes. Yeah. Okay, excellent. Yes. Thank you so much.
Any other question? Yes, Jesus?
A question about the code that is sent across the different modalities. So I understand that the input of the decoder, so the decoder is range level representation, right? So is the decoder, what is like the time resolution that it provides? It's like it transform range level to 4 tokens or to 4 tokens?
So as input, we tried two things. We tried to get, so we needed a multimodal encoder as input. So we tried with the two that we had, which is SAMU XLSR, you've seen. So coming from speech and producing a sequence. And if I'm correct, the frame rate is you have 50 frames per second. And then we tried also with speech T5 that is only English, but that also provides a multi-modal space. And so the frame rate is the same. For the output, actually, it's a much more interesting question because the problem we had with the output, and that's what Henry showed, is that you need to, it's like when you generate speech, you need to have the end of sequence. And that says, okay, that's the end. And actually, one of the problems is really to stop the generation, whether it's for text or for speech. So I'm not sure we can really say now what's the frame rate, I mean, the link between the frame rate of the output of the decoder and really the speech that will be produced after. Because we found out that well, there's still a lot of work to do here. But when you take some embeddings coming from text, for instance, or for speech that the encoder put in this space, of course, the work will be for when going from text to speech, you expect to have a longer sequence as output. When you go from speech to text, you expect a shorter sequence. But actually, we found that our decoder is producing sequences that have more or less the same length or more similar, at least, at the initial encoder. So that means that the information is encoded in a way that is more mixing the modalities, at least in the length. So, yeah, so I don't have an answer, I just have clue.
How do you decide which is going to be the length?
So for the first part of the decoder that is producing a set of embeddings, we have two mechanisms that Henry showed. The first one is similar to what is done in the tachotron in speech synthesis. Is just a linear layer with a sigmoid function, and that as soon as it's above the threshold, you stop the generation. very basic. And the second one is really taking into account the whole sequence that the encoder provides, and it will estimate the duration also according to this the whole sequence. But it's basically except the fact that it sees more information, it's based really on the whole sequence. The mechanism is more or less the same.
But so do you have like two decoders, one that you train when you want to generate this, another one that you train?
The same. It's just the prompt. Yeah, sorry.
So you have the same output for even if you want to generate text or you want to generate speech. So how do you decide which then are you going to use as well to the speech or the
Yeah, so the assumption we do, so the question is, do we have, as we have one single decoder, how do we decide which modality we want to output, and so which lengths we want to produce? And so at the moment, we assume that when you want to do translation, you know what comes in and you know what you want out. So in this sense, you can provide to the decoder the prompts that will tell you, okay, this comes from text and you want to produce speech. And so you give this as input. And we have, so the threshold so far is really empirical. So you need to set a threshold depending on which way you want to translate. So we have one threshold from text to text, one threshold from text to speech, and so on. Yeah. There's still a lot of things to do there. Yes?
Actually, two questions. So when you're including the information, you have like a sense if it's better for female or for male?
Mm-hmm.
This question. So have you tried to, let's say, just have like a gender classifier and thinking or expector to see?
So I would just repeat. Yeah, I would just repeat the questions for the audience online. The question is, do we have similar behavior for male and female when generating speech? And if there's some information that is taken into account here, did we estimate the quality or the output of the generator, right?
Well, for now, we did not, for the TTS systems, we did not do anything multi-speaker. So for now, the speaker information only comes from the training data, which is mono speaker data. So basically, in the end, the speaker is the speaker of the training data. Then we don't have tried with like having just gender identification, but to have like it would be like having only two voices in the end, if I understand correctly. Or,
yeah, something like that.
I mean, it could be maybe something easier to do. I think Jarod did the experiment on.
I was just wondering because in the example that you showed, it seemed that it's like sounds like funny between wait or something, right?
Yes, it looks. It looks a bit like a mixed voice.
Yeah. I was just wondering.
Yeah, so I can say just. Sorry. I can say just one word. I try funny things that mixing X vector coming from male and female, and at the end the speech is like a mix. So you will switch between the word from female voice and male voice, and also it depends on the quality of the speaker encoder. So yeah, in the future we'll try to like work on that and maybe integrate some emotion recognition vector or like speech energy information. So yeah, we're working on that.
Yeah, I was also wondering about that because we were showing also some previous results, but it's nice to see as the examples that you showed and how it will be.
Mm-hmm. Yeah. So one thing also that you we haven't shown here, but we have results. So because the question is where do you take the speaker or gender information from in the pipeline? So what you've seen here is that we use X vectors from the original speech or target language in order to put in the generator. That's when you go from text to speech, you have to do so because definitely you don't have speaker information in the source. If you go from speech to speech, then you can rely on some information from the source speaker. But then what we found out is that the acoustic information that goes through SAMU XLSR, actually you've seen that is is getting rid of the speaker information somehow because it's not optimized for that. And it's also the same for the gender. So at some point you lose really all the acoustic information, so you cannot rely on the one that flows through the pipeline. And ideally, and that's what Peter will discuss after, ideally we would like to keep this information flowing through the pipeline so that you can rely not only on X vector that you inject, but also from the information that really goes from the source. Yeah. But then, yeah, Peter will talk about it. It's not that simple. Okay.
So let's announce a 10-minute break.
Okay, so 10-minute breaks and we'll be back.
At 3:35.
So as Anthony nicely set me up before cookie break started, we're going to be talking about aligning sequences between text and speech. Or as we call it here, constructing a shared modality multilingual semantic space, a proposition for a multilingual speech T5. And if you don't know the speech T5 model, I'll briefly outline it in this presentation. Sorry, I should say I'm Peter Vickers, I'm a PhD student at the University of Sheffield. So what was our motivation? Well, we were in the analysis group for Esperanto originally, and we were looking at language families and things like this. But one of the issues was that the alignment was happening between speech and text, the shared space, if you like, was happening through self-attentive pooling. So you have a sequence of speech frames, you have a sequence of text frames, hidden representations, and you're trying to align these. And so what you do is you say to the speech, you take the speech frame and you have a self-attentive pooling. So you're saying, take some features from this which seem relevant, align them with some features from text which seem relevant. You're not forcing the sequences to align. You're picking subsets to align. And you're getting single tokens which you can't use for lots of downstream tasks. So, okay, this method had very strong results. We have lots of tables of very good results. And lots of the other teams have talked about this. But we just wanted to try basically another hypothesis, another way of aligning text and speech, which was to project the both sequences of text and speech into a shared modality space. One that explicitly doesn't discriminate between the two modalities and that aligns sequences, not pooled representations. So the goal was to kind of, yeah, as I said, devise a multilingual architecture that doesn't discriminate. So we kind of thought about it. We want a system that can take a statement, by which we mean either speech or text sentence, in any language, and produce a sequence of semantic representations, hopefully also maintaining the paralinguistic information from speech, like speaker identity, and produce a sequence that we could then use for downstream tasks. So we thought, okay, how can we actually do this? How can we align sequences with variable length, variable input encoders? Not an easy problem in any kind of situation. So when we were thinking about it, we kind of came up with a system that looked like this. If you know Speech T5, you'll see that this is actually very similar to their architecture. But what we have here is a multilingual speech encoder, XLSR. I think there's 128 languages. It takes an input waveform and generates a sequence of hidden frames. We have a multilingual text encoder, which is going to take a text sentence and generate a sequence of hidden frames, an encoder-decoder network, and then a speech decoder and a text decoder for generating our output representations. Now, we also have in the middle, we have a code book. So we have some kind of bottleneck layer where we're projecting certain frames into lower dimensional quantized representations. And this is basically to try and force the model to learn semantically aligned representations in an unsupervised way. Again, I'll talk about that a bit more in a moment. But you know, as we'll see here, this is the Speech T5 architecture. It's kind of very similar to what we had envisioned. So here, this is an English-only model. This model actually exists. There's a paper on it. You can go and read the results. It's very powerful for speech synthesis and ASR in English because it leverages both modalities. But the only difference between kind of what we're envisioning and this is that they have English-only speech and text feature extraction. So Yeah, I mean, I've been through this already, so we don't need to kind of stay in it for a long time, but we use XLSR and XLMR. So SAMU, XLSR is obviously already using XLSR, so it's similar to the main project in that. We use XLMR rather than LabC because although we have slightly fewer languages, we get informative sequence embeddings out the other end. Okay, so once we've designed our model, how do we actually train it? So we have a bunch of objectives which we inherit from SpeechT5 and some new ones which are designed to encourage kind of robustness when we have multiple languages. So for speech, we've got MELBank, MEL filter bank, log MEL filter bank reconstruction objective, speech unit classification. So this is the Hubert kind of masked speech unit objective, where we cluster our final speech representations with k-means and we mask them. We mask our inputs and we try and predict the clusters for those units. For text, we have masked language modeling, so pretty typical text objective. And we have codebook diversity. So we have this bottleneck layer that we're projecting our hidden frames into, and we're forcing our model to use it and to use it in a diverse way. And then we have some additional objectives. We introduce sequence mixing and mixed modality reconstruction with aligned data to really make sure that our model is learning semantically aligned representations. So this really comes down to the codebook and how it's used. We want a codebook that looks like this, where we're sharing semantic information between aligned statements. So a French sentence, a French spoken sentence and an English written one that have the same semantic content should be using the same codes. We don't want something like this where the model is just segmenting between languages and modalities. So we have the objective from SpeechT5 where we map 10% of all frames to our codebook. But what we want to do is go a bit further and penalize different code usage. So we have the losses we already talked about, but we have these aligned losses as well, which, as you say, are cross-modal and cross-language. So the sequence reconstruction objective is very similar to masked language modeling or the Hubert classification objective. It's that we simply mask more heavily and then introduce a semantically aligned utterance from either text or speech in a different language. So in this example, okay, we can see that we have the cat sat on the mat, but we've masked cat and sat, so the model is not able to possibly guess what should be there, but if it can understand the French, it can see that it should be cat and sat. And we also have an example where this support statement might be a waveform. So the model has to really attend to multiple modalities, multiple languages in order to reconstruct the sequence. We also have a sequence mixing objective, which is more of an explicit spatial alignment objective, which is similar in a way to SAMU XLSR, where we take 10% of the codes from a semantically aligned target, and we minimize the distance between 10% of the closest frames in the target. Turns out that if you kind of really look into this, this is quite a complex thing to perfectly optimize, because we say that you should only minimize the distance for each target code once. So we simplify and just assume that we iterate through the codes in a linear fashion in the target sequence. So the experimental setup that we're working with is recreating the SpeechT5 baseline, then training on English and French in a bilingual setting. Then we're going to look at adding these mixed modality objectives, first the sequence reconstruction, then sequence mixing. And then we're going to add 8 additional languages from CoVOS 2, which are aligned nicely. And we can look at the effects of language families and data sparsity, and also these additional objectives. You can see here that when we add, this is base SpeechT5 and how it performs in pre-training. So we get some nice convergence as reported in the paper. When we add the multilingual feature extractors, XLMR and XLSR, we're getting convergence that's behaving fairly similarly to the base model. So in conclusion, we're exploring the construction of a shared modality semantic space, and we really think the code selection objective, that kind of bottleneck layer that frames are randomly projected into, is the key to creating a multilingual, multi-modal codebook that's going to make sequences align. And we introduced two additional objectives: multimodal sequence reconstruction and sequence mixing objectives.
Hi everyone, I'm Santosh. I'm a postdoc from Brno University of Technology, Czech Republic. And today I will summarize, I will introduce you what we were doing in the last 6 weeks. This is our team of collaborators, and we had two goals. We would like to empirically study the effect of pre-trained language models on low resource machine translation and pre-trained multilingual ASR and language models in low resource speech translation. So in the whole pipeline, we are mainly focusing on text-to-text translation and speech translation. And in our team, we mainly focused only on machine translation and also a little bit on speech translation, and some of our findings align with the existing research findings, and we made some steps in new directions that we would like to explore after the workshop. And to start to introduce our framework, let's say for the machine translation and low resource scenario, we want to go from source language text to target language text. And in our setup, we assume the source language is low resource language. So we don't have a lot of monolingual data. We just have little bilingual dictionary. And the target language is a high resource scenario. We have a lot of monolingual data. We have a bilingual dictionary. And the standard way of doing it is we can train a language model, initialize both the encoder and the decoder, and then fine tune it on low amounts of data. And here, the low resource scenario applies for the source language. So we do not have a lot of monolingual data in the language. We just have very limited and very low amount of parallel data between source to target language. And a similar setup for speech translation as well. So we would like to go from source speech in source language to text in target language. And again, here, the source language is from a low resource family. So we do not have a paired speech and text. So we cannot train an ASR in the source language. And we do not have a lot of parallel data. So we cannot train a very good machine translation system on source language. And target language is, again, it's coming from a high resource scenario. We can train an ASR, or we can train even a multilingual ASR. And this is where what we do, we train a multilingual ASR on target languages. And we initialize the encoder with the speech encoder from the ASR, and the ASR decoder, which contains the internal language model, will be initialized as a decoder in the speech translation. Right? And then we have less amounts of fine-tuning data from source speech to target language, and we use it to fine-tune the model. So that is a setup for the experiments. And then how we were going to implement this or run the experiments or analyze is, first we try to simulate these low resource scenarios on high resource languages. So English to Portuguese and English to German. And in this case, English is the source language, and we would simulate the low resource on the English side. And whatever observations we do on this simulation, we apply on the real low resource scenario, where we go from Tamashek speech or Tamashek text to French text. And to do this simulation, we do this study in 3 different axes. The first one is the choice of pre-trained language model. So either it could be just encoder only language model trained with mask language modeling or causal language modeling, or it could be a sequence language model trained with some kind of multitask learning or hybrid learning. And the amount of, or the kind of data for pre-training, either we could have just unpaired data in source and target language, or we only have monolingual data in the target language, or we have monolingual data in target language and some bilingual dictionary between source and target language. And using this bilingual dictionary, we could construct the pseudo-parallel sentences just by word replacement. And finally, the third axis is the amount of fine-tuning data, because this really affects the downstream performance. If you have a lot of fine-tuning data, we get less benefits from pre-training. If you have less fine-tuning data, we can see more benefits having a pre-trained model. So we also do some analysis in this direction and quantify the benefit of pre-training and different amounts of fine-tuning data. So a little overview on the pre-training architectures that we tried. So the first one is XLM, which uses, let's say, which could be trained with simple mask language modeling. So you have input text in one language. So we mask the input tokens randomly, and then we train the model to maximize the log likelihood of the true tokens at the masked positions. A slight variant of it is called translation language model, in which the input text is basically concatenation of source and target text, and we do the same masked language model training. And this is interesting because, let's say, we have only monolingual text and a bilingual dictionary. We could construct pseudo-parallel sentences and then use it to train this kind of a model. And later. So, and the third one is what we are calling it as hybrid language model. So there are many sequence-to-sequence language models in the literature. So this kind of acts as a proxy for many of these. So again, you can train it with simple mask language modeling or translation kind of language modeling. And then depending on the kind of masking or noise functions here, you could derive several of the existing models like MAS or BART and many other models. And coming to the data for custom language model training. So given the, so we already have a lot of pre-trained models on the internet, and we do not want to repeat the same experiments. So what we did is we trained our pre-trained our language models on limited amount of data, but this limited amount of data is actually in-domain data, which matches the downstream machine translation or speech translation task. And the bilingual dictionary, we used existing bilingual dictionaries for high resource languages during the simulation experiments. And for low resource setting, we made our own dictionaries, and which my colleague Alejandro will talk about.
Thank you, Santosh. Hi, everyone. My name is Alejandro Silva, and I'm a fourth-year undergraduate student at the University of Pittsburgh. And I want to talk about the corpora we made for Tomaszek. Now, before going into the actual corpora itself, I want to give a brief rundown of the language, both the area it's spoken in, as well as some more linguistic details. As you can see, first things first, with the approximate number of speakers, 500,000 to 1 million, that's a wide margin of error. And that's because we're dealing with a very low resource language in an area where there's not a lot of ability to get good statistics. Some sources say it's 500,000, others said 1 million. It was very hard to try and get a grasp as to what is more accurate with the statistics. The data we got was mostly from a book on the dialect of Odolan Tudot and Tamagit, which are both spoken in the African country of Burkina Faso. Now, going on the more linguistic side, Tomaszek is part of the Berber language family. It has 2 grammatical genders, male and female. As for its verb system, it's a consonant root system with infixed vowels as well as prefixes and suffixes surrounding that verb. And for its tense system, what makes it unique in terms of trying to get a translation system for it is that it uses aspects divided between perfective and imperfective, which are further divided in between constitutive and descriptive, making a total of 4 different aspects, which most of our data, I believe, does not use that. And as for the writing system, which was another challenge, there's 3 main ways to write Tomaszek. The first one is a modified version of the Roman script. There's even 2 modified versions of the Roman script, one by the resource we mostly use, which is based on Pras's Lexique. And the other one is the DNA FLA's version, which is part of the Mali literacy program. The other one is a modified version of the Arabic script, which I will show on the next slide for comparisons. And the last one is Tifinagh, which is a script unique to Shamachek, as well as other Berber languages. And on the next slide, I'll give a demonstration of all three side by side. So here's an example sentence. As you can see, they're all very distinct from one another, and we decided to focus only on the modified Roman script due to the fact that first, most of our data was already in that, and second, it's shown that models will perform better when they're dealing with scripts that they're already familiar with, and our model is already very familiar with the Latin script, so we decided to just keep it. But the other two scripts are also worthy to note. Now to get into the actual text corpora we made two main text corpora. The first one is a list of parallel sentences in Tamashek and English, which has about 1,000 entries, and a bilingual dictionary of word pairs from both Tamashek to English and Tamashek to French. All of this data is available on a GitHub repository. If you come and talk to me after the program, I can send a link to it. It is available for use for non-commercial research purposes. And then here below are some, well, before I get into that actually, most of the data was extracted from a book, David Sudlow's The Tamashek of Northeast Burkina Faso. Second edition is a very good book. I recommend it to everyone. And as for some statistics about the data, below you can see the token type and TTR of the parallel sentence corpus and the bilingual dictionary corpus. The first number is the number for Tamashek, and the second number is the number for English. Now, do note, especially with type, that type is almost double for Tamashek what it is English. That is because of the way the author decided to translate things with a many-to-one sort of mapping, with many variations of the same Tamashek word mapping to one English word. So that is something to keep in mind too if you do want to use this bilingual dictionary. And these statistics are for the Tamashek English data sets, not for the Tamashek French. And then lastly, before I hand it off to my colleague Cecile to talk about the experiments, I just want to briefly mention again our methodology. So our goal was to compare the performance of various pre-trained models given low amounts of fine-tuning data. And the way we did this is we simply split the fine-tuning data into chunks where each chunk was based off the previous. So for example, all the data in the 5% chunk was also in the 15%, and so on until they built up to the full data set. And then we ran each split for each model that we fine-tuned. And now I'll hand it off to Cecile, who will describe more in detail the experiments.
So thank you, Alejandro. I'm Cécile Macaire, PhD student in Université Grenoble-Alpes in France. I will present to you the experiment we conducted on this part, as well as the key takeaways. So the goal here was to quantify the benefit of using pre-training language model for low resource simulations. For the setup, we performed supervised machine translation from scratch on different amounts of data, as well as pre-train a masked language model on monolingual data from both source and target languages, followed by a supervised machine translation step. So as you can see here on the English to Portuguese and English to German data set, using in-domain pre-trained language model benefits for low resource machine translation in green. We highlight this part of the graph because in the next slide, we will only focus on this amount of fine-tuning data with different amount of pre-training data. Also, we wanted to compare using a large-scale pre-training language model versus our pre-trained language model on in-domain parallel data. And as you can see between the green and the red plots, in-domain pre-training data is as good as using a large-scale pre-trained language model for low-resource machine translation. For the next experiment, the question was how beneficial is pre-training on pseudo-parallel data. So for the setup, we pre-train masked language model with noisy monolingual data from source and target languages, as well as a pre-trained translation language model with noisy monolingual and parallel data from both source and target language. And we fine-tune on only 10,000 sentences. And as you can see on the graph, you have two lines. So the first line is the lower bound. We pre-train a mass language model on clean text from target language. And the upper bound is pre-trained mass language model on clean text from source and target language. And as you can see, by using this English to Portuguese parallel data, by using this pseudo-parallel data, it benefits for low resource machine translation as we get better results than the lower bound. It's not really the case on the English to German parallel data, so we need more investigation. So to summarize, we saw that using pre-trained language model helps in low resource settings as well as using pseudo-parallel data. So the next experiment was to apply what we have learned on real low resource data, here on Tamacek to French. So for the setup, we use a multilingual pre-trained text-to-text transformer model, so MT5 base. We also train a supervised machine translation from scratch. We also pre-train a mass language model on mono data from source and target languages, as well as a translation language model with mono and parallel data, and we only fine-tune on this Tamacek to French parallel data. And as you can see, by using this in-domain pre-trained language model, it really helps this task of low resource machine translation, but we also need further investigation. So we finish with the machine translation experiment. We can move on to the speech translation experiments. So here the goal was to quantify the performance in low resource settings for speech translation. And the setup is quite simple. So we pre-train an ASR system as an encoder and pre-train a machine translation system as a decoder. And we fine-tune on this English to Portuguese speech translation data. And as you can see here, the less data you have and the less the worse blue score you get. If you use all the data, you have a 45 blue score. And if you use only 5% of the data, the score drops to 9 blue score. And finally, the last experiment was to investigate this multilingual ASR for low resource speech translation. So for the setup, we both pre-train an ASR and machine translation system on only 17 hours of speech and fine-tuning with 17 hours of speech translation and auxiliary ASR data. For the next system, we use a multilingual ASR system trained on 5 languages, and we fine-tune only on 17 hours of speech translation data. And for the last system, instead of using only speech translation data, we only use auxiliary ASR data. And as you can see on the graph on the left, we clearly see that using this multilingual ASR system is really beneficial for low resource speech translation. We also wanted to see, to compare this multilingual ASR system with existing state-of-the-art system on this really challenging dataset Tamacek to French from the IWSLT challenge. And as you can see, our multilingual ASR system performs better than XLSR and XLSR plus MBART. Why? Because the speech encoder and the text decoder are aligned, which is not the case for these two systems. And still, we need further investigation for this part. So to summarize, what Alejandro created as a dataset will be made available, but it's only for non-commercial purposes. We saw that using pre-trained language model on in-domain pseudo-parallel data is beneficial for low-resource machine translation, as well as using a multilingual ASR system with an internal language model is also beneficial for speech translation tasks on low-resource scenarios. Thank you.
But in the meantime, I did have a question. So it's actually for Cecile, because if you want to come back. Go back to that graph which had the blue scores for this one. Yeah, right here. So these first 3 bars on the left, they are based only on 17 hours of on translation data, right? There are only 17 hours of English, Portuguese.
Yes, so English speech to Portuguese text.
Yeah, and then you're getting 15 with that. And on the Tamashek side, you also have a similar amount, right?
Yes, yes.
How come that blue score is 6?
So it could be because this how-to dataset is quite a little bit easier in the sense.
Okay.
So, and that is why we have all the results on how-to dataset are actually quite higher compared to, and that's why we also took another dataset, must say English to German, and even there the results are much lower because it's a little bit difficult. So it could be.
So when you say easy, difficult, you're referring to the answers, meaning the scores are worse. What is the reason? I mean, you know, what is it?
So here one reason is in our pre-trained model, we have languages that are close to Portuguese.
Oh, you do, okay.
Not we don't have Portuguese in here. Whereas in this case, we actually have French in our pre-training data. So the language model kind of knows how to produce French text, and we believe that could give us this benefit. And one more challenging could be that speech of these languages is a little bit different from Tamashek, and this amount of data is not good enough to. Here the challenge is to align this. Let's say the speech encoder would produce some kind of phonetic representations, and we would like to align these phonetic representations into translations of other language. So given this data, the model has to learn to align and translate. And in this case, since it is a different family, we might have slightly worse results. And in this case, things are in same family, and the alignment could have been done easier with 17 hours of data.
Could it also be the genre maybe probably because how to is, I don't call it broadcast speech, but it is intended for being recorded and distributed.
Yes, these are how to video. So
Whereas what kind of function?
I think it is broadcast news,
Oh,
news from radio,
maybe.
and I think this is about 13 hours, and this is 17 hours, so almost the same.
That's a remark I want to make. Evelyn was asking earlier whether you have blue scores or anything. So is this what you're referring to?
We have more.
Also,
there's only one answer to more is done. There is a question. Go ahead, Kevin.
Hi. So I have a question about the M-Speech T5. I think maybe it's a naive question, so I don't quite follow. As you extend Speech T5 to M-Speech T5, what are the challenges or the technical challenges, or is it mainly a matter of just adding more data and making it train?
So I believe this question is for Peter.
I think I need to start
Or
by answering.
So I think the primary concern with extending, like the non-triviality in extending Speech T5 to Speech T5 is that the USP for Speech T5 was that it could leverage completely unaligned data. And as a result, it could be one of those massively it could, I mean, in theory, be a massively self-supervised model that could like leverage unaligned data. But with M-Speech T5, because we're targeting both multimodality as well as multilinguality, there is a need to construct aligned objectives because you want to achieve multimodality and multilinguality at the same time. You want the audio data and the textual data that you have in any particular domain to be aligned, their semantic representations to be aligned. And as a result, you have to then completely negate this USP that like Speech T5 had and move towards aligned objectives. And as a result, also rely on aligned data. which is why when Peter described the reconstruction objective and the sequence mixing objectives, you will notice that there is a reliance on aligned data there. So that becomes one of the first technical challenges. I think the second technical challenge is that since we are now trying to, like Anthony, when he started the presentation, he made this comment that we are making a very strong assumption here that there does exist like a multimodal, multilingual space where you could essentially have all of these representations. But the question is, this multimodal, multilingual representation, what are the dimensions across which it loses out when you are moving from a unimodal space to the cross-modal space? So when speech T5 is a unimodal model. So technically speaking, whatever analysis we have on the tasks for that unimodal model, we can at least hope that when we move from the unimodal model to any modality specific model for that particular language, we will not get too much of a task like performance loss. But at least in the case of this, the strong assumption that we make now with M speech T5, you can sort of assume like an error carry forward. There will be losses because you don't have a modality specific embedding to begin with, but you will also have losses because you don't have a language specific modality, a language specific embedding to begin with. Thomas and Peter, do you want to add something to that? Okay, yeah, Kevin, does that answer your question?
Yeah, that makes a lot of sense. I think there's so many non-trivial extensions, you might as well call it a new name.
Right.
And claim it for yourself, right?
That's a great point. Yeah, we might think of that. Thank you.
Thanks.
There is one more question.
I will repeat the question, but let me go there. So the question is, so in our multilingual ASR, there is an internal language model. And the question is, what if we use an external language model trained only on the target language and use it to rescore the, let's say, lattices or rescore the output during decoding, right? So I think it is something that we were planning to do today, because these are, and we believe it will definitely help. But to be in fair comparisons where all the models are encoder decoder without external language model, we had only this comparison on this slide. But yes, that's it.
And I think Brian's second order question was, will that have the disadvantage that the French you need to produce is translationese, whereas that model will have seen real French? Do you think that's a concern, or you don't know yet?
So I'm sorry, I didn't.
Okay, so what Brian's pointing out is that translated French, meaning something into French, looks very different from natural French, because you tend to stick to certain ways of writing things that was there in the source text.
Yes.
So he's like wondering whether that will become an issue.
I believe it could impact. So we should probably play with the language model weights and even see which part of the language model actually aligns with translated French kind of text and adjust. Otherwise, it could negatively affect. For example, having a French language model trained on Wikipedia could be a bad choice for decoding.
Good. Are we okay in time?
I think if we don't assume that we have 30 minutes of question at the end, we can have questions now.
No, can you go back to? Do you have also the French commandant results?
And the other, we do have results that for speech machine translation only.
No synthesis.
Not for speech translation, because we don't have a Tamashek text from French speech, but we have machine translation results in the opposite direction. But they are about the same, because we do not have Tamashek text to start with. Okay, now I will give to my colleague, Pablo.
So thank you, Santos. Click on this so that it will advance. Yeah, go ahead. So my name is Pablo Jimeno. I'm a PhD student from the University of Zaragoza. And in the following slide, I'm going to be presenting some experiment we've been doing, going from the SAMU-XLSR model and adapting it from different translations. So let me first start with a brief overview of this presentation. As I said, we have been experimented with different speech translation tasks and text translation tasks. The two main tasks we are considering are speech-to-text translation, where we are starting from this SAMU-XLSR model that you have already heard of. And we are introducing an encoder-decoder architecture in order to fine-tune it for the speech-to-text translation task. We are also considering the speech-to-speech translation task, as this was the main goal of this project, and going from speech to speech in different languages. For that, we are considering the direct speech translation framework, where we are using acoustic unit discovery, using a set of discrete targets, and using a completely textless framework. So that were the two different experiments. Additionally, as these were the two main goals of the project, also like using different modalities and under-resourced languages, we also consider first extending the speech-to-speech translation to different input modalities. This is that we made a system that supports both text and speech input and generates a speech in a different language. To do so, we are also using this acoustic unit system in order to make it compatible with our speech-to-speech system. And finally, as some of my colleagues have already talked about, we are using this SAMU-XLSR model. Well, in fact, we developed a new pre-trained model for the SAMU-XLSR using even more languages. And we evaluated on the IWSLT task for speech translation, which tries to go from Tamasek to French. So let me just go back to the beginning of the presentation and try to recap a little bit on the SAMU-XLSR. As you already know, SAMU-XLSR is a speech encoder, pre-trained model that, given an input speech signal, generates a sequence of embeddings. Then these embeddings can be used for any downstream task that you can think of. Some of my colleagues have already presented experiments using it for speaker ID, for phonetic classification, or for even any other task you can think of. Some of the initial assumptions we made for this model, and that Anthony already explained, is that we were using alignment at sentence level. That means that we only had one single embedding for the whole utterance. We are using no decoder, so that we only have the embeddings as they are. And at the beginning of the workshop, we only had experiments on information retrieval. That means that we hadn't validated this model experimentally on any translation task. So now the question is, how do we go from this speech encoder, the SAMU-XLSR, to the actual translation task, even a speech or text translation task? So what we do here is we use the traditional encoder-decoder architecture, which is well known in the speech translation community, using the SAMU-XLSR as our initialization for the speech encoder. And then we incorporate the decoder model based on text, then well-known MBART model that I will describe in the following slides. And then we get those two together in an encoder-decoder framework. And using the speech translation data, we fine-tune both of them for that task. So I will now describe both the encoder and the decoder that we are going to be using for this task. Again, I'm going back to the SAMU-XLSR. This slide is the same as that Anthony presented at the beginning of the presentation. Just let me remind you the basics. It's a cross-lingual model. This version is trained on 51 languages from Common Voice, and it's semantically aligned so that the embeddings from XLSR are pulled towards LabC representations. Talking about the text decoder we are using, we are in fact using the MBART model, a pre-trained text model that we will be using to initialize our text decoder. So once we have both the encoder and the decoder initialized, we're going to be fine-tuning both on the speech translation task. But in fact, we are not fine-tuning all the parameters in the model. We are doing it in an efficient way using adapters, as you can see here. Instead of fine-tuning all the layers in the model, we're introducing this adapter here, and we're only updating the parameters in these layers. So that makes a significant reduction in the number of trainable parameters that goes from 700 million to 56 million. Okay, moving on to the experimental setup for the training data, we are mainly considering the COBOS dataset for the speech translation and the CBSA's dataset for the speech-to-text translation. Both of them come from data from the Common Voice initiative, and they feature 21 languages to English translation task. In our experiments, we are also considering 3 different subgroups. We are separating in our results high resource languages with more than 100 hours, low resource languages with less than 10 hours, and then medium resources, the ones that are in the middle. So I will now show you our results on the speech-to-text translation task first. Let me first explain you what you are seeing here. We are measuring our performance in blue score, so the higher the better. And we are also considering 3 different sets of experiments. In this first one, we are training a single model. We are fine-tuning the encoder-decoder using all the 21 languages in the data set. So the conclusion we get from these experiments is that SAMU-XLSR significantly outperforms XLSR when used as a speech encoder for this task. And this improvement comes mainly from the medium and low resource languages. Okay, so the following experiments now try to use bilingual models. That means that instead of using a single model trained on all the data, now we're going to get each one of these language pairs. That means going from Spanish to English, for example, and we will train a model on that data. In this slide, we are comparing the performance of the multilingual model, the one I showed just in the previous slide in blue, with the bilingual model in green, trained only on that specific language. So what we can see here is that in some of the languages that were getting the worst performance in the multilingual model, get a huge boost in performance when using this bilingual model. Okay, so our final experiments on the speech-to-text translation task was aiming to do zero-shot translation. I will explain you now what we mean by zero-shot. In our experiment, what we are doing is we are taking the languages with more than 100 hours. This is the the high resource languages. Once here with more than 100 hours, we are training a system only on those, in this case, 4 languages. And then we are testing on the other languages in the data set. So that means that the model hasn't seen any of these languages in training. So these are the results for the zero-shot on the medium and low resource. Again, we can see the similar conclusions as the one we were getting in the previous experiments, where the SAMU-XLSR speech encoder outperforms the XLSR model in the speech-to-text translation task. So that's it about the speech-to-text. I will now move on to the actual goal of this project, which was a speech-to-speech translation. So for that, we are adapting this direct speech-to-speech translation framework, which we call it's called direct because it's not using text at all. We just go directly from speech to speech using these acoustic unit systems that are extracted from target speech. I will now describe how to get these units. For the speech-to-unit translation framework, we are using something similar as the one in the speech-to-text framework. Here is the SAMU-XLSR speech encoder, and instead of using the MBART version of the text encoder, we are using an MBART which is trained on units. Concerning the speech generation, my colleagues already presented this hi-fi gun that tries to generate audio signal directly from these acoustic units. So how do we get these acoustic units? It's basically a quantization on top of a speech encoder. As you can see here, we start with the target speech and we go through different speech encoders. We say different speech encoder because we have done an experiment with a bunch of them, but in fact you get the output of the speech encoder. And with that, you apply a k-means quantization. And with the number of clusters, you can also control the number of acoustic units you are considering in that system. So for the output, we get a sequence of IDs for the clusters. And in the final step, what we do is we collapse the repeats to remove the repetitions in this sequence. So that's it. That's the targets we will be using for speech-to-speech translations. Okay, so as Anthony already mentioned, there's still some question remaining how to evaluate a speech-to-speech translation. Some members of our team are working on that, and they will tell you later in the following part of the presentation. But we needed some way to evaluate our system. So we used this evaluation pipeline that you are seeing here. We start from the source speech, and from that source speech, we predict the acoustic units. And with that acoustic units and the hi-fi GAN model, we generate the target speech. And in order to get the blue score, what we do is we run an ASR system on top of that target speech that generates a hypothesis text that will be compared using the blue score with the reference text. So this is the blue score we're going to be using to show our results. Talking about results, this is our results on the CBSS 21-2X translation task using this direct speech-to-speech translation framework. Let me just first explain you what you are seeing here, because it's a little bit tricky. Now I'm highlighting in red the speech encoder used as initialization for the speech-to-units framework. This means that it's a blue line means that we are using the XLSR as initialization, and the green line means that we're using the SAMU XLSR for initialization in the speech encoder. Now I'm highlighting in blue the speech encoder used not in the translation part, but in the acoustic unit discovery system. That means that each one of these blocks is using a different encoder system in order to generate the acoustic units. So now that you know what you're seeing, I can tell you that in general terms, we can see again that SAMU XLSR outperforms XLSR as a speech encoder in the speech-to-speech translation task. However, what we can also see here is that SAMU XLSR obtains the worst performance when used to extract acoustic units. You can see here, these two lines here belong to the SAMU XLSR used to extract the acoustic units. We are also showing here in the orange line the cascaded system, which is the concatenation of a speech-to-text translation system and a TTS system. You can also see there that none of our system made it to beat the cascaded performance. So this is another experiment we ran on the speech-to-speech translation. In this experiment, we wanted to show the influence of the number of acoustic units. This is the number of clusters in the K-mean quantization. We are experimenting with 100, 500, 1,000 units, and using the SAMU XLSR speech encoder only here, and for two different systems used to extract these acoustic units. We didn't find any consistent trends when increasing the number of units. You can see here, for example, that for the M-Huber system, we get the best performance for the 1,000 units, but this doesn't hold when used the speech-to-5 system. So we cannot say that we get a better performance when increasing the number of acoustic units. Okay, so that's it about the speech-to-speech translation results. I will now move on to one of the important goals of this project, which was the multimodality. So we saw that we had a system that was able to go from speech-to-speech in different languages. And considering that we wanted to have a multimodal input, we thought, okay, what can we do now to support this multimodality? The first idea was to extend it so that it could also accept text inputs. So now we could go from a speech to speech or from text to speech. In order to do that, we tried to minimize the number of changes to the current system we were using. So this is the previous speech to speech translation framework. And in order to go from text to speech, we are going to be using the same acoustic units. These acoustic units predicted from the target speech, and we are going to be incorporating this new branch here that will accept text as input and will try to predict the same units as an output. So this can be seen as a machine translation task where our input language is text, and our output language is these acoustic units, these discrete units. One of the advantages of this system is that the hi-fi GAN is shared among the two modalities, so we can generate text from those units even if the input comes from the speech or the input comes from the text. Furthermore, the same evaluation pipeline we were using for the speech-to-speech framework applies here, so we don't need to do any changes to that. So this is the results for the text-to-speech translation framework. Let me just first tell you what we are using here as initialization. We are considering two different text encoders, the MBAR25 and the MBAR50. These are basically two different versions of the same text model. MBAR25 was trained with 25 languages, and MBAR50 is the bigger version with more languages of the same text encoder. So in general terms, what we see here is that we obtain a better performance using the MBAR50 with what somehow was expected because it was training with more languages. And we also saw that some languages in the CBSS test set are not in the haven't been used to train the MBAR25, but they are in the MBAR50. So this is better seen in this graph here. Even it's too big, but I'm going to explain it. Now in red, I'm highlighting the languages that are not in the MBAR25 version, but they are in the MBAR50 version. And as you can see here, for example, for the Farsi, is one of the languages that gets the better improvement when going from the MBAR25 version to the MBAR50. This happens also for most of these languages highlighted in red. What's also interesting is that some of the languages in the CBSS test set are not in MBAR25, neither in MBAR50. But even though we are also getting a significant improvement when using the MBAR50 model. Here, for example, for the Catalan language, which was underperforming using the MBAR25, and gets a significant boost in performance when using the MBAR50. Even if the Catalan language is not in the MBAR25 or in the MBAR50 set of languages. Okay, so that's it about the text-to-speech translation. For the final part of my presentation, I'm going to be talking again about this Tamasek to French speech translation task. Anthony and some of my colleagues already explained this, so I will just remind you a little bit. This data comes from the IWSLT 2022 evaluation campaign, specifically from the low resource speech translation task. And for that task, participants were given 17 hours of parallel data from Tamasek audio to French text. So in order to handle this data, in the final weeks of this workshop, we developed a new version of the Samuel Celesar model, which was trained with even more languages than the original one. Now we are going to 60 languages instead of 50, which was the original one. For that, we also including the data from the Babel dataset and this Tamasek data has just explained. With this new version, we evaluated it on this Tamasek audio to French text. Let me just first show you some previous results. I think they are the exact same that Santosh showed a few minutes ago. So this is just the blue score from Tamasek to French for the system that participated in the original challenge. And as you can see here, the best result was 5.7 blue score using a WAP2BEC system trained with in-domain data. So these are the results we've been talking about for a while that you were expecting. We evaluate here the previous version, the original version of the Samuel Celesar with 51 languages, and the new version trained with 60 languages. And as you can see here, we are setting a new state of the art on this task with a 13.2 blue score. So just some conclusions to sum up. Through all these speech translation and text translation tasks, we've seen that Samuel Celesar outperforms XLSR when used as a speech encoder as an initialization in this task. We also set a new state-of-the-art in the speech-to-speech translation for the CBSS dataset that tries to go from 21 languages to English. We developed a multimodal input translation system with competitive results that is able to accept both speech and text as input. And finally, we also set a new state-of-the-art in the Tamasek to French speech translation task with this new version of the SAMU XLSR with 60 languages. So that's it. Thank you.
So when you added the Babel data set,
Maybe Antoine, you know about that. We are just adding it to the training pool and retraining everything from scratch, I guess.
We are just training everything from scratch with new languages. That's it.
What did you say about noisy data? Yeah. Yeah.
Yeah, there is some noise. Oh, so the question was how did we do to train the new SAMXLSR model with Babel data? So we just use them. we just got the data, prepared them using the KD recipes that we had, and then we train a new system from scratch using those new data and also the training data for the Tamasek IWSLT task.
Okay, so I guess you didn't have time to do analysis.
No, we did not analyze. No. But you're right. There is some mismatch because also it's some conversational telephonic speech, so there is mismatch. But yeah, it seems to work.
Yeah, I was going to add that I think I'm loud enough for the online. That Babel data isn't particularly noisy. It's just telephone, and because it's conversational and collected in real life, not in the studio, it has natural background noises, but it's not noisy as noisy.
Well, no, it depends. Like I remember for the camel data, there was a lot of package loss, and there are different varieties of camel as well. So it's not uniform across, but it's not that. So, but it's definitely a lot of heterogeneous characteristics.
Yeah, we did not listen to the data.
Yes. No, yeah, exactly. It's patchy. Some languages, and also it depends a little bit on the collection platforms. I think
yeah, so it's not that homogeneous. I remember some languages really bad.
Okay.
I have a quick question regarding MBARC 25 versus MBARC 50. So when you add like the same amount of languages again, do you also have like 100% more data, or how much more data do we add when we add the other 25 languages?
In fact, we didn't train the embarked systems like we were using the pre-trained model just as an initialization for the text-to-speech systems. And in all the experiments, we were using the same data for the fine-tuning. We were using all the 21 languages in the CBSS data. I don't know if this answers your question.
I was more thinking about how many utterances or how many words were added. So did you add like 100% more words when these 50 languages versus 25 languages were used, or was it less? Because I could imagine that not every language is equally represented in the training data for that one.
I think we have to look at the
yeah.
more detail.
The thing is, we didn't dig deep into the embarked system because we were only using them as an initialization for the text-to-speech system, and we really can tell you about the details.
Just a quick question. I was checking to make sure on the internet, but the original XSLR 53, is this already part of common voice? So would you specify like what data from Babel or like what?
Yes. So we did not use the same set of languages than the one that was in XLSR. We just used Common Voice 8, and we restricted the amount of languages by taking only the languages that was also supported by LabC. So it makes a total of 51 languages. So at the beginning, we did not add any Babel data in the training. Yeah.
For the last segment for today, before the general conclusion, I'm Olivier Galibert. I haven't been a student for a long time, but since we didn't have any Andy to do the presentation, you're stuck with me. So this segment is how to evaluate speech translation with a text. So what does that mean? We want to do a textless metric. We want to compare a speech hypothesis with a speech reference along euphoria several axes. The main one is meaning. We want a similarity score between those two samples, in fact, and to see if they actually mean the same things, since we want to evaluate translations. And potentially, we want to have other axes for analysis, like if the voice is similar, if it's a similar gender, for instance, similar speakers and prosody, things like that. But that's secondary. The first thing is meaning. And the idea is to build this metric by trying to have a strong correlation with the current text metrics that are used in the domains, such as BLEU, CHRF, etc. So if we can create a speech metric that correlates with the text metric, at least we have a good part of the job done. And why do we want that? It's because first, to evaluate a speech-to-speech translation system, we don't always want to fall back to a transcription. And a good reason for that is that for some languages, like Tamashek, for instance, we can't easily fall back to a transcription because we don't have them for the references. And more importantly, like we said before, roughly 50% of the languages of the world have no written form in the first place. So if we want to work with them, we have to be evaluated without having a written form. And incidentally, if it works, we're not there yet, we can use also that to build a training objective for speech-to-speech systems directly, so that they don't have to have the loss built on the text. We could have a loss built directly on the speech. So how to do that? We have two approaches. The first one is see if we can somehow reuse the existing metrics on the text. For instance, you take BLEU, it's comparing the presence of n-grams of words between the hypothesis and the reference, computing precision, etc. And we could say that n-gram of word, in fact, is a segment of speech. So if you have segment of speech that are in the hypothesis, that appear in the reference, it's good. And it's possible to compare segments of speech, at least in theory. So maybe we can create things from the speech, which we can use the metrics on it from the metrics on. The other way is to learn a system to predict the score directly from a reference hypothesis audio. So for the text metrics reuse, the idea is to build the pseudo sentencing using the symbols, audio symbols, extracted by clustering audio features, and then reuse standard text metrics. So as the generated audio, the reference audio, you generate features, then you do a k-means, a deduplication where you remove the repetitions. So you have a string of symbols. We are bored with numbers, so we use kanji, but it's just symbols. And then you compare these using BLEU or CHRF or whichever metric you like in translation. So the audio features, that could be either pure signal processing features like Cepstrum, like we get from Librosa, as used in SpeechT5. We can have cook features, but that are hopefully language independent, like the result of wave to wave 2. You have a number of symbols, number of clusters to decide. So we tried with 10 to a lot more. Anthony could tell you how much CPUs that used. And the distance between the feature can be seen as Euclidean or as cosine, depending on the kind of features you have. And if it works, and that's a load-bearing if, it should behave like the text metrics. It should be easier to have in language-independent fashion because if you have signal processing features, it doesn't depend on the language. And if it works, should be similar to phones. So there's a way to interpret them, more or less. So we had a nice experimental setup. We use Common Voice for English because, in fact, when you want to do that, you only want to see if you're able to see whether sentences are similar, looking at the speech, having the text as reference. So you don't need to be the result of the translation. You just need, in fact, ASR data. Well, ASR training data. So we have 800,000 occurrences in Common Voice 4, and we compare the sentences to each other to each other to get a good range of metric values. In fact, we have 35 million pair of sentences where the blue value between them is non-zero. That means it has at least a quadrigram in common. So that's nice. We have data to work from. And we've made extracted the features, made the k-means, made samples, completed the metrics, and we created scatter plots to see the level of correlation. If it correlates weight, it should be on the diagonal, since we put blue on text on the bottom and the blue on speech vertically. So here is what we get. You can see the beautiful diagonals. You can see it's not completely wrong in the sense that from left to right, you have more and more clusters. So that means it can be a lot more random. So the blue on speech is decreasing because it doesn't recognize the n-grams. And other than that, well, that's not a metric. So the result on the Cepstrom feature, that was only the Cepstrom feature, they are barely distinguishable from noise. It's not informative at all. We are computations going on with more clusters and wave-to-wave-to features, but I'm not holding my breath, to be honest. It could work on the wave-to-wave features, but I'm not convinced. The conclusion is that k-means are not going to spontaneously separate the actual contents, which we could say the words or the fonts of the words, from all the metadata, the speaker characteristics, the prosody, the pitch, things like that. It's not going to separate them, so it's not usable to do a text metric afterwards. So, well, we did the other version, which is a train metric. So to build a train metric, we were inspired from Comet, which is a machine translation metric on text that tries to predict human evaluations. We did an equivalent for speech, where you take the reference and the hypothesis speech, you make units with Hubert von Dam, then you use an XLM Rosetta to make an encoder, you pull a feed-forward layer, and you try to predict the metric you want, CHRF in that case. And why doing that? Because, well, learned metrics are more and more present in the literature, often to predict human judgment because humans are expensive, but why not trying to port a metric from one media to another? The difficulty is that this probably needs to be trained on multilingual data to actually be language independent. And it's a lot more black box, so it's a lot harder to explain, in fact, the results, to know where the limits are, because you can't really analyze what's going on, you just have numbers. So we had an experimental setup with synthetic speech coming from CVSS, where the synthetic speech was transformed to create new speakers from them and to change the contents a little, messing with the embeddings. So that's slightly dissimilar transcripts. You can see the score distribution for CHRF on the original, which is a lot of pair sentences are identical, and you have a number of them which are not. And we're trying to learn CHRF on the speech using the text as reference. And as a text-like pipeline, we just applied CHRF to the speech unit extracted by Hubert. So the results we have. The first line is the reference, the CHRF on text. The second line is you take the XLM Rosetta to predict the metric, to see if XLM Rosetta is actually capable of predicting a CHRF. And the answer is yes, because you have 0.9 correlation on Spearman and Pearson. So that means, okay, XML Rosetta is capable of trying to predict that kind of metric. Then we tried an equivalent of what we did before, but on Hubert 50 audio samples, and we just did CHRF on these samples without training, and we got a 0.4 correlation, so that's bad. So at least it keeps being bad even with different features. And then we tried actually learning the system using the occurrences, and you can see with N of epochs, it's not that many, and Hubert 200 samples, we are rising to 0.7 correlation, which is starting to be rather good. And you can see the distribution of scores are similar. We can reproduce the distribution of CHRF scores on the test from audio compared to the text. So that's nice. So with the learn metric, we have promising results. We are currently training on the non-synthetic speech. And in fact, we had preliminary result last night. And we're currently on the development data at 0.9 correlation. So it's more than promising. There's a good chance it's going to be a very good metric, but it's only one epoch yet. So we're going to see how it goes. And well, we probably need some hyperparameter tuning, like the type of features, the number of symbols, things like that, because we're not entirely sure what the influence is going to be. And we haven't tested the portability to other languages at all. And that's going to be the main point. If we train on English, it's going to work. Is it going to work on French, on Japanese, on Tamashek? And that we don't know yet at all. So we really need to test and manage the language portability. Probably going to try to leverage the language family that were analyzed by the other subgroups. And we're probably going to try other network structures, trying to remove the quantification in the middle. What happens if you don't have symbols in the middle and you go directly from features to the pooling and etc. And maybe even trying to interleave the hypothesis and reference features to enable direct comparison by the network, not having a pooling in the middle, but trying to have CNN or something like that directly compute on the audio features. And if we had that working, we can even try to put other features like the speaker information prosody similarity, so the other axis on which we would want to evaluate the generated speech. And that was it for the evaluation part.
Ask Evelyn again if you
No, she cannot talk apparently. Like
oh,
if you can move the questions.
Oh, okay, all right. So Evelyn has some audio trouble. She's asking, can you send me the email of the presenters? Yes. Can I have access to the data on GitHub so you can answer her? And then finally, can we use the S2S or S2T system, i.e. comma check to English or French, meaning she wants to use the system. Anyway, these are all follow-up questions. Anthony, you can be the point man for this.
Yes, sure.
Yeah.
And there was a question for the evaluation part.
No, I guess I killed everybody already.
Actually,
yeah.
I have a question about that. Do you guys also consider the speech quality? I mean, it's the current kind of analysis is more for the, how to say, the translation quality, right? So I just want to have a discussion.
Yeah, it's probably possible to do speech quality. I think this approach is not going to work as is because what makes speech quality right now is not the content, in fact. And these features try to extract the content, at least the learn one try to extract the content and remove more or less what it sounds like. So it's probably possible to train a system, and there are challenges on that to evaluate the quality of a TTS, more or less. But it's going to be different criteria than what is used by a system that want to look at the meaning, because it's completely an opposite approximation, in fact.
Yes, yeah, thank you so much. Yeah, I actually wanted to mention that, yes, as you mentioned, the TTS people now working a lot for the such kind of objective measure and the voice most challenge.
Absolutely.
It's actually has a, I would say it's a limited experiments, but seem to have a good success in terms of the predicting the most from the DNN. But of course, your problem is, the multilingual problem and so on.
Yeah.
And not sure this kind of the conclusion can be applied to it. But I'm looking forward to your kind of further investigation for this direction. Yeah, thank you so much.
Thank you.
Anyway, there is a small but important way in which speech translation actually has an advantage, which is that all the proper names, they don't need to be translated at all, just reproduce them in some sensible way. Like when you said in French, Anthony, that my name is Anthony, I didn't get any of the French, but I got the Anthony. And if you just replace that, it's going to be fine. So
if you
you
use
have to think about maybe
if you use speaker in China, I don't think it's going to work very well.
say that again.
If you use speaker as a tone name in China, it's not going to work out very well. It's Beijing there. There are translation of proper names.
No, what I'm saying is that in terms of what you measure, right? The text translation might be wrong, but you could get the speech right.
Oh, I see. Yeah. That could be fun, yeah. Okay.
Yeah, so I'm going to end up this afternoon with some conclusions. So takeaways after this long presentation, you already have many things to note, I think, I hope. So, well, I wanted to come back to the initial question and the assumption that we've made about the cross-modal, cross-lingual space. And because I was afraid that someone would ask, so does it exist at the end? Well, honestly, you can guess I don't have the answer, but definitely from the semantic point of view, there are some promising things, and I think the progress made on the translation, but learned with the semantic information, shows that there is some avenue there. And I was wondering actually about the translation of certain concepts, because even for the concept, actually, some things are not translatable. Like hugely, for those who speak Danish, it's a word that I don't know how to translate in French because we don't have such a concept. I was trying to understand how to translate train on time in French. We don't have the concept either. So there are a couple of things like this. I don't know how far we can go. One thing we have shown here is that the way we have addressed the question so far doesn't preserve the acoustic information from the space. And so it's normal because most of the work has been done to preserve the semantic, and you can expect that, well, speaker, emotion, everything is noise when you think about semantics. So definitely there's some work to go there in order to improve this and to maybe make a space that is more structured to preserve different type of information. Regarding the work on the under-resourced languages, I think we can be happy of the results that the team got during the workshop. And well, as you can see, I think there are a lot of things to dig into the slides and future work to do, but we can see that the progress brought from adding languages or adding techniques also benefit for other languages. So I think there's some ongoing work to do for the language families to understand, because we can see that if you add language from one family, it doesn't benefit, especially this family sometimes, but others. So definitely there's a work to do maybe with linguists on this aspect to understand why one language benefit to another and not to something closer. We have a lot of remaining questions, for instance, and not only questions, but problem to address in the community, because we've seen many progress on the task of translation from many language to English. And I think we have good results on this. But the thing is, as soon as you want to produce, to generate in an under-resourced language, then it becomes much more complicated because we don't have data. And obviously, we are in a domain that still relies on data. So if you want to generate, for instance, Tamacek, it's more difficult than to translate Tamacek into something else due to the data. And so we still have questions, already talked about it, about the family-specific models. Then I think there's a huge work that must be done regarding the cross-modality in using different kind of alignment other than semantic only. And that's what Peter presented. And regarding evaluation, actually, I was very happy this morning to see the results from the team because, well, Olivier just said that we have good results, promising results on the train matrix. But now we need to see how language portable is this metric. So can we train it for well-resourced languages and use it on under-resourced languages? That's another problem, and maybe we'll have time in a couple of years to work on it in a future workshop. Yes, so that's the work of this big team, totalizing 29 persons from different horizons. And well, I would like to thank the team member today and for this work and the atmosphere. Just a few numbers about the team to finish. So 27 scientists working for 39 days with 34 cookie breaks, actually one less because yesterday they complained I made them miss one. Just 20 hours of Harry Potter screening in the same room, 109 hours of karaoke cumulated, I would say too precise. And you can see 100,000, more than 100,000 hours of GPU, and the same about CPU computing, which makes us, according to my number, liftable from 5.17 tons of carbon produced during these last 6 weeks. And around that, you can see that I have the same virus as Sanjeev. I noticed that on the first slide. We had also 7 cases of COVID, but which were well managed thanks to GHU's organization. And yeah, I want to finish like this to thank the local organizers. There are not so many in the room, just a few, but there are also others outside, and without who this work wouldn't have been possible or in such good atmosphere. So now we can take a few questions. I think we still have some time. Come back to something more. Yes.
I have a question. Since you're combining speech, which for example, a lot more tokens or symbols that you then translate into another speech. So, did you do an analysis where actually the translation suffers more, for example, longer sentences, shorter sentences, or something like that?
The question is, did we make this analysis on the duration of sentences?
Yeah, which sentences are easier or is more difficult to translate?
Well, so I will turn with the people who really made the experiment, but I think I can answer that during this workshop, if I'm correct, you didn't do the analysis because we just had 6 weeks very intense. But if you ask them, maybe there will be that's something they will consider. Yes. Well, I don't know. Yeah, no, that's not something we looked at. I'm sorry. Yes, Shinji?
So I have a question about the how to say strategy. You guys actually try to work on the, for example, the unit, the trend from the self-supervised learning or whatever, in the source side or target side, right? And then my question is that we also have a pony, right, which is well defined unit. So do you guys have some kind of comparisons or some how to say that why you guys take the strategy of this unit rather than pony?
Well, I think there are different reasons. The first one that comes to my mind is that we've been trying for a couple of months to synthesize speech from phoneme posterograms for the purpose of having some being able to put some human in the loop in order to modify and to have something that the human can understand really. And so far, we don't achieve a very good performance, good quality speech with this approach. So that's one point. I think the second one is more related to the architecture of the network. And I think, well, maybe you can correct me or you want to answer?
It's related to the state of the art.
Yeah, it's related to the state of the art and available models that that we could reuse for that. Yes.
Please next time repeat the question.
Ah, yes, sorry, excuse me. Yes, Paula?
No, I've checked. There is it.
So actually, I have 2 questions. So probably as suggested, it would be nice to have, let's say, what's the translation from, let's say, French to language or to other resource language and have, I don't know, all the different things that you found that were interesting in the first part to be included in that final presentation.
Mm-hmm.
I think that would be like quite interesting if at some point you can get that much. So that is like one thing that I would like to see in the future. And the other question, you mentioned at some point that I mean somebody in the group mentioned that you were trying to get the text units closer, or yeah, text units closer to the speech units. But you didn't mention how. I think it was.
Yeah, you want to? So the question was, we tried to get the speech unit closer from the text unit closer to the speech units. That was for the text to speech translation. Yeah. And okay, how did we do that?
Maybe I explained it wrong, but the idea is to try to translate from the text to the same units we were using in the speech-to-speech system, so that then we can just use the same vocoder from those units. So then we can reuse the same vocoder structure just to synthesize the speech from the units.
I see. Okay. So brilliant. I understood.
Yeah. So actually, that's one work that still has to be done, is to join the text to speech and speech to speech, because we have results on both, but we rely on different models, and they definitely that would be we need to have joint fine tuning in order to really get a unified system, but we didn't have time to do that yet.
So follow up, the speech and text are paired, or you don't have paired?
So the question is, the speech and text, are they paired, or we don't have pair? For the specific training of text to speech, well, text to unit. So yeah, they are paired. Yes. Okay. Yes. Antoine, you want to add something? Yes. Sorry. Yes.
So I guess you have mentioned a point about this, but the common space has mostly semantic information, not the acoustic information from the speaker and some other characteristics. Right? So, what directions can we take to that information?
So the question is, the common space is now based on semantic information, and how can we include some more acoustic information, whether it's speaker or emotion or prosodic? Well, actually, I just got an email from Nigel who offered to discuss about that, because there are different options, different paths to take. Well, definitely, we need to, at least, if we don't really rethink entirely the encoder, we need at least to add some more objective functions for the training, because so far it has been really trained just for one task, which is semantic information extraction. So for the acoustic, we've seen in the results that some information is still there, like for ASR, but it's just that it's not well structured so that the system are able to use it properly. I mean, simple systems. Depending on the downstream system you put from this common space, you might get good result in ASR, or you can get very poor results depending on the complexity of the system. So I guess the question is, how can we have the same thing with simpler system for each task? So, well, definitely we need to, the information being there, I think we can already get some more information just by structuring the space, by adding some loss functions dedicated to this. Maybe we would have to, one idea that has not been developed during this workshop, but that was originally proposed, was to really structure the space, like having embeddings with different dimension and forcing some dimension to retain some information while other dimension will focus on something else. And maybe have some kind of merging at some point, because those information are not totally disentangled. So that's maybe one way to go.
On your last point, I actually wanted to make a comment. This has happened several times that people look at these large models, the path to Vex from Qberts, and they talk about where is information for speaker discrimination or phoneme recognition, and they show these graphs where something goes down and back up, and so they always use the 6th layer. So I just wanted to caution people not to say there is information here and less information there. And the fact of life is you can never create information by processing anything. You can only destroy it.
Yes.
And therefore, if a layer in the middle seems to have less information and that there's more information in a later layer, it's because you're not measuring it, because the later layer cannot restore that information if the layer earlier did have it. Yeah. Therefore, for any processing, which is the best layer, the 0, yes, because the signal is still there. So I think what you said about the power of the machine that then does, for example, in Natalia's case, right? So the probing device is the one that is limited.
Yes.
It cannot use the information as presented in one layer as opposed to another.
Yeah.
So especially there are students among us. So don't think that information gets generated again afterwards. It's always there. It's just that whatever model you're using to do inference cannot exploit it.
Yes.
I mean, to give you an easy example, if you think there is less information in the 7th layer and it shows up in the 13th, well, all you do is you send your data from the 7th layer to a machine whose first 6 layers are the same as the 6 layers from 7 to 13, and you've got that information back. So if you're not able to do it from the 6th layer, but you're able to do it from the 13, it's because you don't have enough power in your machine.
Yes.
So everybody keep that in mind when you think about these things.
Yeah, for the speaker information and emotion information, we had this debate because really depending on the architecture of the downstream system that you plug in, you can really have very different results. That's the case actually for the ASR. If you look at the slides again, for the ASR information, we have two different systems, which is very simple with BLSTM. Well, there have been some fine-tuning also done there, but this system is really performing better for one type of embedding, while the other, which is more classical and without the fine-tuning of the encoder, performs very poorly. And definitely that's this.
No, you answered very carefully. I didn't want people to miss the subtlety.
Yeah, definitely. Thank you. Yes, Paula?
So how good is any of the systems that you presented in following the correct grammar in the target language?
Guys, that's for you, this one.
I didn't want to put you thinking that there is like a difference between English and Spanish and of course French, right?
Yeah, so
and the grammar is so different that sometimes even when we try Google or whatever, these automatic systems, sometimes they don't do a very good job.
Yeah.
So I was just thinking of.
So just to repeat the question, Paula is asking about the correctness of the grammar produced by our system. I'm afraid we haven't checked really carefully this. I mean, we didn't measure this yet, but definitely that's something that is worth looking at, especially when we look at the family of languages, because that's something you expect maybe to be improved by languages that are related. So far, no, we don't know. But
so the translation is just word.
The translation has been measured only with blue metric, so it's you can get very poor grammar. Yes. Yeah, definitely. Yes. Yes, Santosh.
To answer this question,
Come down.
So to answer this question about the grammatical correctness of the output, so if we use large language models, they can produce grammatically correct sentences, but they may not be the correct translations. So in the sense, the outputs are, in my opinion, could be grammatically correct, but may not be semantically perfect translations, according to one reference translation.
I think you said, Anthony, that you didn't really do a lot of analysis, but did you at least look at some of the sentences to see if they give you some gist of what was in the input?
So I think at least for the speech to speech, we've listened to a couple of samples and they were quite good actually. For the text, we also looked at examples, right? So I think they spent a lot of time checking the output of the system. Of course, not everything, and not measuring very strictly with metrics and quantity of data, but definitely by hand.
I don't know if there is really metrics.
Yeah.
I was thinking about things like, since these are news stories, you could categorize them. This is like, international news, or this is a crime report. So would you get the gist of it? Would you get the topic right? You could build a topic classifier based on in fact, you don't even need any ground truth. You could just take the reference translations and group each thing into one of 20 topics.
Yeah.
And then see if you can reproduce that based on the translation output.
We still don't know if it's going to be
Yes.
No, it doesn't answer Paula's question. I'll bring up a different aspect, namely that, grammar is hard. So Santosh was saying, hey, at least you want to get the content right. And my reaction was, well, if you want to worry about the content first, the adequacy of the translation, then let's see if it classifies topics correctly.
Yeah, actually referring to Nancy's talk about the topic with a sliding window, I think there's some things to do regarding this also. Could be interesting.
Because this data is broadcast, I'm sure there are some standard classification pieces anyway, and if not, like I said, you can do it fully automatically.
Yes.
When we look at the topic level, I guess depends on how you define the topic, because the topic might be true, but the nuances might be off. So
yeah, you could do it at any level of detail. You could say, like, 6-way classification: sports, domestic politics, international politics, arts and craft, or whatever.
But if it's on the topic level, and say I like baseball, and then in French it's I don't like baseball, then it's semantically opposite, right? So although it's the same topic, but
yeah, that's what I'm saying. So that translation to me is very good for certain things. Namely, if I want to build the incoming audio into, okay, here is my sports specialist, and here is my politics specialist.
So do you think that they will follow the same grammar, or it's just another?
It's not a matter of grammar. I was thinking, you can measure, classically when people try to evaluate translation, they think about the adequacy of the translation. Does it capture everything in the input? And the fluency of the translation. Is it fluent in the target language? And how to measure adequacy has always been a challenge. And actually, so has both have been a challenge. But one way to think about it is, are you talking about the same general topic? If you are, at least you're in the ballpark. Then give me an alternative.
I don't know. I don't have an alternative.
If you don't have an alternative, then
yeah. So I have it. This one. So let's talk about it next year a little more.